Hey everyone, am I audible?
Yeah, you're audible, sir.
Okay. So welcome to Naxxatra's event today, and today is very special because we have two really amazing guests. The first session, as you know, is it's titled as "Capturing the Invisible Universe," and the second session is scheduled for 8 p.m. And it is about amateur astrophotography, and it is by Akash Simha. So those of you who want to attend both sessions, we will give you a 15-minute break after this first talk, and then you can again rejoin the link. So yeah, the second session again will start at 8 p.m. Both the sessions are streamed on our YouTube channel, so you can check that out. I think the link is on the chat box. So for those of you who are here for the first time and you have not heard of Naxxatra before, we are basically a collaborative student community, and we started off just about a year ago. And initially, we were having a lot of study groups, in topics like cosmology, photometry, observational astronomy, and so on. So we gradually grew as a community, and today we have a lot of students and professors and mentors who are basically research scholars who help us in collaborative projects so that undergraduate students can get a early exposure to research techniques. So that is our goal today. So we try to offer a lot of opportunities for young scientists who want to do research in the future. And our main goal, like today, is to connect experts in the field to people who want to enter the field in the near future. So without much further ado, I think we can start off the session. I would like to introduce first of all Sagar, a friend of mine who played a key role in putting all these events together today. And I also want to mention that today marks the beginning of our summer programs. And as you might know, our theme is multi-messenger astronomy. So throughout the summer till June, we will try to have as many events as possible. These need not be just lectures. We have contests and treasure hunts. We also have projects and courses. So just stay tuned. If you've not joined the WhatsApp group, you can, and you'll get all the updates there. So Sagar has been a really committed mentor and student in our community, and he's been leading a couple of projects as well. So Sagar, over to you.
So, hi everyone. Thank you for joining our webinar today on capturing the invisible universe through observational radio astronomy. So today we have a very special guest from St. Joseph's College, Bangalore, who is also my teacher, Dr. Rabbi Akibangiras. So Dr. Rabbi is a passionate professor who has done his MSc from IIT Bombay and got his PhD from got his PhD for kinematical and spatial ellipsoidness in spiral galaxies from Raman Research Institute, Bangalore. So in today's lecture, sir will be talking about observational radio astronomy and also non-optical bands through radio astronomy. So I hand over the call to Rabbi sir.
Thank you, Sagar and Naxxatra, for asking me to deliver a small talk. One second, let me just share the screen once again, because I somehow that came out. I presume that you can see the screen now, right? All of you?
Yeah, we can see it, sir.
Yeah, fine. Let's. All right. So the lecture is going to be paced at a very elementary level, actually, because Sagar told me that a significant number of you people are from BSc or PUC background. So if I scare you with equations, generally many people will get turned off from astronomy. So let me just make it as a fun kind of lecture. If you have any doubts, perhaps you can ask in the chat box. And maybe I'll ask Sagar or somebody who's a co-host to stop me if some questions arise, so I can answer it and then keep on proceeding. It could be just like a college lecture rather than a very formal kind of a lecture. Okay. So today I'm going to talk about something called as capturing the invisible universe. Okay. So invisible, what it means is that in non-optical bands. Okay. So this invisible out here basically means non-optical band. Okay. Bands. So I'll be talking about those things. So let's start with basically why we study astronomy. So the points are basically astronomy is one field where anything which you study, whether it is physics or mathematics, chemistry or electronics or computer science or even biological sciences are useful, and you can actually apply in astronomy. Second thing is it provides us with a lab to study phenomena which are not seen under terrestrial conditions. See, that I'll explain it a bit more bit more detail later. The third thing is basically the only thing which restrict an astronomer is basically lack of imagination. Okay, so because universe, anything which is not explicitly forbidden by physics could happen in the universe. Okay, so that gives you a wide opportunity to apply your physics knowledge or mathematics knowledge or any of this knowledge into studying an object. Okay. Then another very interesting thing about is basically you can go to very exotic locales and collaborate with very interesting people if you become an astronomer. For example, I have friends who go to Hawaii to do observations rather than being a tourist. Okay, and if you go to, like, I started my career as a particle astronomer. So as a part of that, I had to go to, for example, KGF. I have worked deep underground in the mines to do observational astronomy. You'll be very surprised about that, right? So these are all things which you get chance to visit exotic locales, collaborate with people, and not only that, it is extremely great fun. Okay, astronomers are the nicest set of people I have worked with. They are fun people to be around with. Now, you should be also aware of the constraints astronomy has, because every field there will be advantages as well as disadvantages, the constraints in astronomy. The most important thing is basically the objects are not amenable to laboratory studies. If you do an experiment in lab, very often you will get repeatability. If you mess up the experiment, you always have a chance to do the experiment once again. In astronomy, that is not possible, okay, very often. Then the second thing is basically in astronomy, you get information in these three modes. That is basically in the form of electromagnetic waves. You will get information from particles, and you will also get information from gravitational wave, which came in about 3 to 4 years back. Okay, so these are the only ways in which you can get information about an object, a celestial object, in the case of astronomy. Okay, and astronomers are restricted, especially the observational astronomers are restricted by sky conditions and man-made interference. For example, when I am a radio astronomer, since I did my PhD in radio astronomy, the cell phones which we use very commonly now is a bane in the case of radio astronomy. Okay, so this is a problem, big problem for astronomers. And if you are staying in Bangalore, you will see that the sky conditions out here, light pollution, for example, it will affect us extremely. And nowadays, you would have heard about the satellites which are being launched for GPS positions, interfering with the astronomical observations. And these are all challenges an astronomer has. And we also have a duty to make people aware of this interference, which actually make our job extremely difficult. Okay. Now, why do we study these objects, celestial objects? So the questions which we usually deal with is basically the following. What are the physical processes that give rise to the observed phenomena? Okay. So this physical processes is something which is challenging for us to understand. The second question is, which you should always keep in the back of mind, is basically, are the laws of physics universal? Is the law of, let's say, gravity, which we have quite well understood on terrestrial conditions, is it valid in Andromeda galaxy or a distant galaxy? Does it apply, or does the physical laws change with respect to time? Does the physical laws change with respect to different regions of the sky? For example, is the law of gravity towards Andromeda galaxy, is it different from Andromeda galaxy to, let's say, a galaxy named NGC 1309? Okay, so these are all questions which astronomer has to think about. Basically, are the laws of physics universal? Are there physical laws which are yet to detect in terrestrial conditions? Are there some special cases which you might have? And you might also start wondering whether are we alone in the universe? Are there extraterrestrial life existing somewhere else? These are all things an astronomer basically thinks about very often. Okay. Now, before I proceed further, I have to make it very clear to you. The very fact that if I look at you people, assuming that you people, I am able to see you people in real life, what are the conditions which you should satisfy for the very fact that I'm able to see you? Okay, so the first condition is that the object under study should emit or reflect or scatter in some part of the electromagnetic spectrum. Okay, so just to refresh your memory, the electromagnetic spectrum, when I'm talking about, it could extend from the high wavelength region, which is basically the radio part, all the way to gamma rays. Okay, so gamma rays are basically extremely high energy radiations, or even further down this range, where you have TeV, tera electron volt particles, which is coming from the sky. Okay, so when people say an astronomy, generally we will be dealing with the visible region. Okay, most of the astronomers will be dealing with the visible region, whereas I have done my work in this branch, basically in the radio branch, and to understand certain other aspects, you should also have a physical idea about what is the kind of typical wavelengths which you're talking about. So the wavelength in radio can extend all the way from a few centimeters or microns in certain cases, because there is no sharp boundary saying that this part is radio and this part is microwave. Okay, so please keep that in mind. Sometimes even microwave will be treated as part of the radio astronomy. Okay, so you should have typically an idea about what is the sizes of the wavelength or length of the wavelength which you're talking about. When you're talking about radio, it could extend from a few microns to a few meters. That means sizes of a human being or size of the building. That is the typical wavelength which you're talking about when you're saying that I study in radio waves. Okay, so that is what is being shown here, this part, this typical size. Whereas visible radiation, when you're studying, the typical sizes are basically that of the bacteria. Okay, or if you're doing research in ultraviolet astronomy, you're basically dealing with sizes of the molecules. If you're studying about X-ray astronomy, you're basically talking in terms of sizes of atoms. And gamma rays will be typically the size of the nuclei of the atoms. Okay, so this you should keep it in your mind roughly, so that you will appreciate what we are going to do later. So just to refresh once again, the condition for seeing you demands that the object should emit, reflect, or scatter light. That is one condition. The second condition, which is basically is that the intervening medium between you and me should be transparent to that particular radiation which is being studied. Okay, so for example, if you are studying, if you are emitting in radio, let's assume that you people are emitting in radio, and I have only a detector called I, which can detect only invisible, then I will never see you because you are emitting in radio, right? Whereas my detector is basically capable of detecting only invisible. That means I will not be able to see you at all. So that is another third part which I went ahead. Okay, so the detector should be capable of detecting that part of the spectrum which is being emitted by the object under consideration. Okay, so for example, if you have if you are a radio astronomer, you have a detector which you can see here. This is one detector. This is another type of another. There are 4 detectors here in this particular telescope. Okay, which is capable of detecting in 4 different wavelengths, which actually lies in radio part of the spectrum. Okay, whereas if you are looking at this particular detector, which is basically in X-ray or UV, you will see that detector, the shape and size of the detector is completely different from what you see it in the radio waves. So here we have a gamma ray detector. This I think is a X-ray detector. I've forgotten which one it is. Okay. Now, why do we do this kind of studies? Okay, so this is my favorite cartoon about people trying to figure out, blind people trying to figure out what is an elephant. Okay, so a person who is touching the tusk of the elephant might say that elephant looks like a spear. Okay, a person who is figuring it out, the ears of the elephant will say that elephant is like a fan. Okay, a person who is actually figuring out about the body of the elephant will say that it may be a wall. Okay, or a person who is handling the tail of an elephant will say it may look like a rope. Okay, so different people have different idea about what is an elephant look like. Okay, so when you observe a celestial object in different wavelength, this is precisely what you're doing. Okay, you are looking at a celestial object's different features. So you combine all these things together, you might get a picture which might look like this. Okay, it might be looking at an elephant. You put together all these things, and you might get a shape which might look like this, which is not too bad, but it is completely different from the actual reality. Okay, so but you are getting closer and closer to the actual reality by observing an object in multiple wavelength. Okay, so that is the reason why modern astronomers generally don't restrict themselves to a single wavelength. They actually study in multiple wavelengths the celestial object. Okay, now before we proceed further, one thing I should tell you is this is a rule of thumb. Okay, the size of the detector should be roughly lambda by 4. I presume that all of you know what is lambda. Lambda is the wavelength by 4 of the wavelength in which you are detecting it. So for example, if you have this is a radio detector, okay, and this is a gamma ray detector. So which one do you think will have a bigger size? Okay, so you have basically radio wavelength, which is basically ranging from centimeters to meters. And here you have basically 10 to the power of 15 meters. Okay, roughly. When you say gamma ray, the photon's wavelength is roughly about 10 to the power 15 meters. Here, in the case of radio, you have typically the wavelength stemming from centimeter to meter. So just by this analogy, you will see that the detecting part out here will be a few centimeter. The detector should be of a few centimeter to meter size. So you will actually see the detector size to be that much. Whereas in the case of a gamma ray thing, you have to basically make it interact with the nucleus of an atom itself. Okay, so then only you will be able to detect a gamma ray. This thing. So the size here will be huge, Whereas size here, which may be a gas particle, the nucleus of the gas is basically made to interact with the gamma ray. Okay, so detector size and the wavelength in which you detect are closely related by this particular relation, lambda by 4. It's a rule of thumb. Okay. Now, another thing which you should remember is basically, if you are trying to image an astronomical object, you will basically have a telescope attached to it. Okay. The telescopes will be very weirdly shaped in often cases. For example, if you have an X-ray imaging device, you will have a telescope which might look like this. You might start wondering what is happening out here, right? It doesn't look like any mirror at all, which you are used to. Whereas this is an X-ray mirror, basically. These are concentric X-ray mirrors. Okay. So here what is happening is basically an X-ray photon comes, hits this mirrors at a grazing incidence, and then it gets focused onto a detector, which is a CCD camera, X-ray CCD detector. Okay. So this will be an X-ray CCD detector. CCD means charge coupled device. Okay, charge coupled device. So this is how a X-ray imaging telescope will look like. Whereas this is how a radio telescope is going to look like. This is basically a radio telescope which is available in Australia, which is called as Parkes. So this Parkes telescope is basically a big, massive dish. So this dish is used to collect information about the radio, and then they will try to collect the information at the center here. Okay, this is a receiver. So now what is happening is you have a radio light coming and striking it here, and then it gets collected onto the receiver. So I should actually put the arrow mark. So let me draw that. Okay. Now, what is the reason for having a telescope attached to an imaging system? There are basically two reasons. One is basically the most important thing is basically collect large amount of photons. So you have a larger telescope, it will collect more and more light. Okay. Then it will bring to focus these collected image. So if you collect large amount of photons, basically what you are basically saying is that I can go to fainter and fainter object. Okay. Fainter. So fainter objects can be detected. Okay. That is the reason why you go for a larger and larger telescope. For example, with your naked eye, you might be able to go to a 6 magnitude object if you have perfect sky conditions and if your eye is perfect. Whereas if you have a telescope, which is let's say a 1 meter telescope, you might be able to go to about 15 or 16th magnitude in a good place. So you are basically seeing fainter objects when you have a bigger collection area. Okay. And the second reason is basically, you should always ask a question, why do you have to have a mirror which is parabolic in shape? Okay. So the reason for that is basically when you are collecting the light, you see this light ray coming and striking it here. If you have a parabolic shape, all the rays are going to reach the receiver in phase. That is not very often stressed. Light reaches the focus in phase, basically. Okay. So if it is reaching out of phase, then you have a problem because you might have learned about interference and things like that. But if it is a parabolic shape, all the light is going to reach the detector in phase. Now, this also implies that you need a surface accuracy. Surface accuracy means the surface should be, suppose I draw a surface, the irregularities on the surface should be less than 1 lambda by 4. basically. So for example, if you have a 20 centimeter wavelength, okay, in radio, just 1 second, give me a minute. If you have a 20 centimeter wavelength, you should have a surface accuracy 20 by 4 centimeter, which approximately makes it at 5 centimeter, right? So if you have a radio telescope which is working at 20 centimeter, the surface accuracy, irregularity on the surface should be smaller than 5 centimeter, basically. Whereas if you have an optical telescope, which might work in about 5,000 Armstrongs, I'm just arbitrarily putting in some value, 5,000 Armstrongs, okay, then the surface accuracy should be less than this value, right? So that is roughly about lesser than about 12 Armstrongs or so. You calculate it exactly, you will get it, okay? About 1,000 Armstrongs, right? Roughly. So that is the reason why optical telescopes will be polished to a great extent, whereas what happened? Whereas radio telescopes need not be polished to that kind of an accuracy, because radio telescopes can tolerate much less surface accuracy. Now, the second thing which you should understand is basically the information about a celestial object you get is very often through the spectrum of the object, okay, not by taking a picture. You will get certain amount of information about the size, shape, etc. of the object if you take a picture, but the physics comes from the spectrum usually, okay. So you have to understand this part also. Let me just remove this writing. I'm sorry about this delay. So, for example, if you have a object, a solid, hot solid object, or extremely dense object, it will basically emit radiation in all directions. Okay. So, if you study this kind of a hot solid or a liquid or a dense, it is basically going to work like something called as a black body. Okay. So, if you take the spectrum of that object directly by sending it through a prism, you basically get a continuous spectrum here, as shown here. Okay, so this is going to be a continuous spectrum, which you are going to get if you take the object, okay, directly, the spectrum of that object. But if the light from that object is passed through a thin cloud of gas at a temperature which is lower than this, okay. So here, let's say the temperature of the black body is T1, and temperature of the cloud, let's say, is this a T2. If T2 is less than T1, that is the temperature of the gas cloud is, let's say, 100 Kelvin, whereas the black body is at 1000 Kelvin. Then if you observe the light coming through the gas cloud, you basically get an absorption spectrum. Okay, so you'll see dark lines in the spectral thing. Whereas if you look at it, gas cloud in this particular direction where the source is not visible, if you're looking at in this direction, there's no source, right? So the light which is coming in this direction will basically have emission lines. Okay, so you understood how do you get the continuous spectrum, an absorption spectrum, and an emission spectrum. Okay, if you have a gas cloud which is coming like this. So this is how you take a spectrum of an object. Okay, and spectrum contains basically the physical processes, information about the physical processes which are happening in the object, celestial object. Okay, so if you have a black body kind of a spectrum, okay, you will see that if the emitted photon has got a temperature, I mean, or energy which is less than kBt, okay, you are basically in something called as the Rayleigh regime, and then the emitted power basically depends upon the temperature of the object directly. Okay, Now, this is a very important aspect. For radio kind of work, this is the regime which you are working in, basically. Okay, so that means the photons energy is actually much smaller than the temperature. Okay, so we will usually be working in the Rayleigh jeans regime, whereas if you are studying in X-rays or something like that, you are actually in the Vane's regime, where you have this kind of a picture. Okay, so if you are in quantum regime, that is basically when the energy of the photon is much higher than the temperature of the object. You have the quantum regime. There you will deal in photons. We will always talk about photons. Whereas here you will basically talk in terms of wave fronts. So that is something which you should remember. So in radio regime, you will talk in terms of wave fronts, whereas in X-rays, you will talk in terms of photons, okay? Photons and their energies. So this is a picture of the sun taken a few years back. So you can see the sunspots here. Okay, these are our sunspot, and these things are called as plages. Okay, so you can see these things, and this is it taken in visible white light. This is a white light image actually. But astronomers have the freedom to give whatever color they like to white light. Now, just to make it interesting, if you look at this image, what are the important things which strikes you? This, I presume that since I cannot talk to you, if you notice the central portion seems to be brighter, right? This region is brighter. And whereas this region becomes darker. Now, just by looking at this picture, all of you would have guessed that the central region is brighter than the dark, towards the edge it is darker. This is actually a true phenomena. It's called as limb darkening. There is information about why you should actually wonder. I'm not going to give you the answer. You should wonder why the central region is brighter in comparison to the limb. Okay, limb is darker. So this is for you to ponder about. So you will start wondering about small things like this, and that will actually get you into astronomy. Okay. Now, sun, the actual spectrum of the sun is basically will look something like this. Okay, this red thing is what you're actually going to see on the surface of the Earth. Okay, at sea level. So you will see lots of dips here. You can see this kind of a dip. These are basically going to be the absorption bands or absorption lines. Okay, the yellow, what you see out here, is basically the spectrum of the sun if you take it outside Earth's atmosphere. Now, if you look at this spectrum, you will see that these lines, this strong absorption which you see in the red line, red part, is not there in these regions, right? That is outside of the Earth's atmosphere, you don't see this kind of absorption lines. So this will give you a clear indication that these absorptions are not coming from the sun. These are actually from the Earth's atmosphere. Okay, so you will identify lines like this. Okay, you're basically comparing the spectrum of the sun outside of Earth's atmosphere with that of the spectrum of the sun which you get at the sea level. So automatically you will know that the cause of these absorptions are basically Earth's atmosphere, elements present on Earth's atmosphere. Okay, and then what people will do is basically they will try to fit a black body spectrum through the spectrum of the sun that outside of the Earth's atmosphere. Okay, so you see a black body spectrum. Okay, this is going to be called as the black body spectrum. So knowing the black body spectrum, if I know what is the peak happening, you have something called as Wien's displacement law, and you'll be able to guess what is the temperature of the sun. Okay, so from the spectrum of the sun, you guessed what could be the temperature of the sun. And if you look at the absorption lines, which you can see here, that will give you information about what are the elements present in the sun. Okay, because this absorption has to come from the sun, assuming there is no intervening medium between sun and earth. If there is an intervening medium, then you might even ascribe this absorption to that intervening medium. Okay, so the spectrum basically gives you lots of information about what is the composition of the sun, what is the temperature of the sun. By looking at the depth of the absorption lines, you'll be able to even tell how much of material is present there in the sun and so on. So spectrum gives you lots of information about the physical processes and composition of a celestial body. Okay, so you should remember this. So another great importance about the spectrum is basically this. This is basically, you're going to study the magnetic behavior of the sun. Okay, so if you look at the sunspot here, this is corresponding magnetic field. Magnetic field of the sun. Okay, so you will see that corresponding to this, there is some magnetic information about it. Corresponding to this sunspot here, you see magnetic information. Okay, and here, if you look carefully, you will see some plages and some weird part is seen here. Okay, so how do you detect this magnetic field from the spectrum? So that's what I'm going to discuss now here. So what you do is basically, let's say this is basically a sunspot. Okay, so you put a spectrometer on the sunspot, spanning from, this is going to be called as the photosphere, and this is basically the sunspot, and you basically put a slit of a spectrometer here and study the light coming out of it. Okay, so this line is basically in iron, highly ionized iron, I think Fe24 or so. That is the iron line, which is ionized 24 times or 23 times. Usually the spectroscopic notation is basically one less than that. For example, if you write hydrogen and in bracket 1, this means neutral hydrogen. Hydrogen atom. Whereas if you write hydrogen with a 2 inside, this means singly ionized. Hydrogen. Okay. So this is called, when we call as spectroscopic notation. So if in our case, the line is taken from iron 24, that means 23 times ionized. Okay, so you will see that outside the sunspot, this appears to as a single line. Okay, the spectral line looks like a slightly broadened, but inside the sunspot position, you see that single line is basically split into 3. Okay, this is basically going to be called as Zeeman splitting. So people who have studied atomic physics will learn about Zeeman splitting. That is basically in the presence of magnetic field, the spectral line corresponding to this is getting split into 3. Okay, so how much is this splitting happening? How far away? What is the separation between these lines here? That will basically give you an idea about the strength of the line, magnetic field. Okay, so by studying the Zeeman splitting, you will be able to guess what is the strength of the magnetic field which is there in the sunspot. So that is how you develop this kind of images, which is actually going to be called as the magnetogram. Okay. So by studying the spectral lines, we have basically able to find out what is the strength of the magnetic field. So additional information now. We know from the spectral line studies, what is the temperature, what are the materials present, how much of material is present there. If there are magnetic fields, you are able to study what is the strength of the magnetic field and so on, right? So spectrum contains lots and lots of information about the celestial object. This is something which you should be very clear about, okay? Now, this is something exactly the same thing which I have just explained to you. So you know what is the peak line, and knowing the peak line, you will be able to find out what is the temperature of the celestial object and so on, okay? Now, the most perfect black body which we know is basically the cosmic microwave background radiation, CMBR. This is the most perfect black body which we know, okay? So this is taken from FIRS data, okay? And the error in the measurement is actually smaller than the width of the line, okay? It is so tiny. So we had to show the error bars. These are basically the error bars which you see here. These error bars are 400 times sigma, okay? This is the 400 sigma error bar. And the peak happens at 2.75 Kelvin, okay? Now, just for the curiosity's sake, just 1 second, I see some chat questions. Okay, this we'll discuss later, these questions. Okay. Now, the interesting thing is basically the black body spectrum. Let me ask you one question, simple question. If I was teaching you heat and thermodynamics, maybe I would have asked you one question. Suppose you want to draw a line. Let's say you have a, suppose you have a XY coordinate. This is Y axis, this is X axis. And if I want to define a straight line, you basically need to have 2 points at least, right? To connect a straight line through 2 points, you should minimum know 2 lines, okay? 2 points. Then only you will be able to find out what is the slope and what is the y-intercept. And once you know that, you can always write y is equal to mx plus c. That's the equation. So to know the straight line, you need to know at least 2 data points. The question which I want to ask you is, how many data points are required to plot a black body curve? Okay. So this is something, again, something which you can think about. How many data points are required to plot a black body curve? Okay. This is something for you to think about. It is quite interesting. If you remember your black body curve, you will be able to answer this. I given you the information that it's a black body. So how many data points are required to plot a black body curve? You should think about it. Now, let's go to studying something called as the revolutions which happened in astrophysics. It all started with a guy called Carl Guth Jansky. Okay, so he's the father of radio astronomy. So what had happened is basically he was when transatlantic radio signals started going, roughly around about the time of Second World War, there were stray interference which people observed. Okay, especially people who are interested in sending radio signals across Atlantic. So they asked Carl Jansky to find out what is the source of this interference. And he built a radio telescope. This is one of the first radio telescopes which we know of, which is basically a dipole antenna. Okay, so you can see this kind of structure here. This is basically the antenna. Okay. So there are multiple of them. So these are all dipole antennas. And this dipole antenna is mounted on a turntable. You can see that it can be rotated about the wheel. This is called as a turntable structure. The reason why you have this thing is basically the perpendicular to this dipole. If you get a signal, then you will be able to get a signal. Okay. But if the signal is coming in this direction, you will not get, that is along the axis of the dipole, you will not get a detection. Okay. So by rotating it around, people will be able to tell precisely in which direction is the signal coming from. Okay. So if the signal is there in this particular direction, as the telescope is arranged in this direction, you will get a receiver signal. But if the signal is coming from the terrestrial side, that is, if it's coming along this direction, you will not be able to detect any signal. So by rotating this around, you will be able to tell in which direction is the interfering signal is going to come. Okay. So this was done by Karl Jansky, and he first detected this kind of a signal, which you can see. And you will see that this axis is time axis. Okay. This is a strength axis, signal strength axis. I'm just calling it a signal strength. So you see that there is peaks here, periodic peaks. Okay. At about 10, 15, there is a peak, 10, 20, there's a peak like that. So, and he was able to say that the direction of the signal is what is shown here. You can see that it is south. This is again coming from south. This is again coming from south, and so on. Okay, periodically. So people started wondering where is it coming from, and he was able to tell precisely that these radiations are coming from the southern direction, from outer space. Okay, so this is basically due to, now we know that these are basically due to our galaxy itself. The galactic disk, when it's passing over the sky, then these bumps are seen. Okay, for each, and the antenna was rotated every 20 minutes along the circle. So periodically, you'll see every 20 minutes these bumps appearing wherever the galaxy disk was. So this was the first detection of basically an external source emitting in radio waves. Okay. Now we were lucky in this sense. This is basically transmittivity. What you see out here is basically the atmospheric opacity. Okay, so if you see an opacity high here like this, that means the radiation is not going to reach us at all. So whatever wavelength is coming here, it will not reach out us. We are standing here, okay, at the ground level. So if the opacity is very high, you will not get the detection. If the opacity is low, for example, here in this region, you see that the opacity is low, almost zero. That means whatever radiation is coming from outside will reach us here in the ground. And we were lucky in the sense, the first detection what happened actually from radio. The radio waves actually reached the ground level. Okay, suppose Jansky had actually done this experiment in, let's say, X-ray, sitting here, then Jansky will say no source is there which is emitting in X-ray. We would have known, we already knew about the optical this thing because light from the celestial objects reach the ground level. Okay, but suppose instead of doing radio astronomy, if Jansky was asked to detect interference due to X-ray, he will say no external source will be, external source is giving rise to X-rays. Okay, so that is the reason why it is a very serendipitous discovery. Basically, we are lucky to say that there are sources sitting outside Earth's atmosphere which is emitting in radio waves, not only in optical but in radio waves. So this opened up other fields. Basically, people started wondering if radio waves are being emitted by external sources, will they be emitting X-rays? Will they be emitting gamma rays? Will they be emitting IR? And so on. Okay, so these people started wondering about it just because we opened up a new window to the universe, which is in radio. Okay, so now to understand these things in a bit more detail, you should understand the spectrum. So if it's a black body spectrum plotted in a logarithmic graph, okay, this is basically log. This is also a log-log graph, basically. Then the shape of the blackbody curve will look somewhat like this. So you notice this thing, the slope is a positive slope for this curve. Okay. So whenever you detect something in a spectrum, you actually try to detect it in, find out the slope of the spectrum. Okay. The interesting thing is basically, if you compare the spectrum of the object, it's not getting clear. You will see that in the slope direction is negative here. In the previous case, where you had a blackbody curve, the slope was basically positive, whereas here the slope was basically negative. Okay, this is actually spectrum taken in X-ray. Okay, so X-ray spectrum is basically negative slope, whereas out here the slope is positive, blackbody curve. Then you should start wondering what kind of physical process is giving rise to a slope which looks like this. Okay, so this is what I meant by wondering, when asking you to wonder about what are the physical processes which are happening out here. Now let me look at radio specifically. So these are the instruments which we use. This is actually a telescope facility called as VLA, which is there in New Mexico. So you can see the parabolic dish, and these dishes actually can be moved around in railway track. So you can see that it can be moved around in railway tracks. Right now it is parked in something called as the D array. Okay. So these telescopes are parked in very close to each other. Can you see that? So, but these telescopes can be moved around on railway tracks. Okay. This is a telescope which I often use, which is going to be called as the GMRT, okay. Giant Meter Wave Radio Telescope. Now you have an enhanced version of the GMRT. Now here, if you notice, the parabolic dish seems to be transparent, right? Because unlike the VLA has got a filled surface. You remember the surface accuracy which I told you about. So for example, if you have a 20 centimeter wavelength, the surface accuracy should be lambda by 4, which is equal to 5 centimeter. Okay, so you can tolerate a surface irregularity of 5 centimeter in the case of radio telescope. But in VLA, since they have lots of money and their budget is very good, they have decided to go for filled telescope. Okay, now GMRT, which is in near Pune, you have this telescope facility. There you don't have a filled array. You have constraints, not only finances, but also you should understand this weight of this telescope is pretty heavy. Okay, it may be almost close to that of a railway engine. Okay, about 6 tons, or a truck. Imagine the weight of a truck, or slightly more than a truck's weight, and you want to move it with precision, like hairline accuracy. Okay, you want to move it. So if there is a filled array, breeze can catch it. So it will become more and more difficult to hold it very rigidly. Okay, so to avoid these problems and budgetary constraint, we decide to go for surface accuracy, which is slightly less, a few centimeter. Okay, 1 to 2 centimeter. So that means you can have holes which are basically 1 to 2 centimeter. This thing. So they have filled it up, even though it looks like a empty space. It is actually meshes. There's a mesh here whose holes are basically of the size of 1 to 2 centimeter. Okay, that is quite interesting. Now, any observer should also know these things. The basic concepts are in optics. Basically, angular resolution. You would have learned this thing as basically delta theta is equal to 1.22 lambda by d. We forget about this. So angular resolution basically depends upon lambda by d. That means if you have two objects which are separated and they subtend an angle delta theta, they will be just seen as separate object if you have this condition satisfied. Okay. So this could be one star, this could be another star. If you want to see them as two separate entities, you should satisfy this condition. Now, this is the third reason why we go for a telescope. You want to improve the angular resolution, but that is not a very big constraint in the case of optical telescope, but in radio astronomy, this is quite important because of this reason. You want a angular resolution of 1 arc second. 1 arc second means you want to say two objects are separate if they are separated by 1 arc second. Okay. And we are making this observation in, let's say, 20 centimeter, because my observations were mainly in 21 centimeter actually, that is H1 line, atomic hydrogen line. So I am partial to this 20 centimeter. That is the reason why I always put 20 centimeter. So if you want this kind of a resolution, okay, at a wavelength of about 20 centimeter, then you need to have a telescope which has got a diameter of roughly about 41 kilometer. Okay, that's a huge telescope. Now that is not possible to have this kind of resolution, whereas optical telescopes, to get this kind of resolutions, it's quite an easy thing to do. Okay. Whereas radio wavelength, by virtue of having the observations being carried out at higher wavelengths, you need to have a telescope whose diameters are basically about 41 kilometers. So this was not possible to build a telescope like that. So we were quite innovative. So before that, I'd like to just tell you another thing. So here what you have is delta lambda by lambda should be of the order of delta V by C. Okay, this is the Doppler formula which astronomers very often use. These are the two things which you should know: the angular resolution and the Doppler effect. Okay, so if you know these two things, then you can build up a telescope. So what we do is basically we synthesize a telescope in radio astronomy. This is going to be called as something called as an aperture synthesis, or to be very precise, it is going to be called as Earth rotation aperture synthesis. Okay, so what you do is, imagine that you are looking from the top. You are looking in this direction, and you have two telescopes which are sitting here. Okay, so what you do is basically you measure the flux or specific intensity of the radiation coming, and you note down what is the time of arrival of the signal at this point. Okay, so if you wait for 24 hours, what happens is that these telescopes are going to rotate from west to east in this direction. So as a result, if you are looking from the top, what you're going to see is that over a span of 24 hours, these telescopes have built up a circle. Okay, this is telescope, this telescope builds up this, and this telescope builds up a track which may look like this. Okay, so if you have a Y-shaped distribution of telescopes, so you can see this VLA. I told you about the railway tracks. The railway tracks are like this. So now what you have done is basically you have arranged these telescopes in the shape of a Y. In 6 hours, okay, why 6 hours? That is something, again, you have to, this thing. Then you can build up tracks like this, and you are basically building up a telescope. Okay, this is actually GMRT building up. So in GMRT, you are basically building up a telescope which is roughly about this diameter. Okay, and this size of the telescope is usually written in terms of wavelengths. So suppose I'm observing in 20 centimeter, 21 centimeter actually, 20 centimeter. You are basically measuring this one distance 20 from the center, that is this portion. You have 100 kilo into 20, right? So that is the size of the detector. So 20 centimeter, so into 100 kilo into 10 to the power 3, that is basically for the kilo, into 100, that is basically into 10 to the power 2. Okay, so we have built up basically a telescope of this size by doing this kind of a rotation. Okay, so you can see that it is basically, this length is basically 20 kilometers. Okay. So because this one goes with this, basically we have a telescope whose size is basically 20 kilometers this side, and you have 20 kilometers this side. These are actual data, basically, what I'm showing. So you have built up a telescope using the GMRT like this. And this is something which I have already told you about, basically lambda by 4 and the whole size, which is basically equal to 5 centimeter. And here you have another telescope array, which is called as WSRT, okay, Westerbork Synthesis Radio Telescope. Here, what we have is basically an east-west array of telescope. Basically, you can see that this is from east-west direction, one single array. In VLA, we had a Y shape. In WSRT, you have an east-west array. Again, you can build up a telescope, which is quite the same. So what are the important discoveries using the radio telescope? You can have this one. This is something which I mentioned to you. This is going to be called as CMBR, Cosmic Microwave Background Radiation. These are two famous scientists who won the Nobel Prize for this detection. This is Penzias and Wilson. Okay, they are the people who discovered this. Then many of you have heard about this lady, Jocelyn Bell, who discovered basically the first neutron stars or pulsars, as they called it. This is her detection, actual detection. You can see that this axis is basically time axis, and you see periodic blips. Okay, this kind of blips are seen. This is basically a pulsar. Okay, pulsar detection. And recently we actually imaged it even using X-ray. This thing. So you can. I'll show you the image later. This is basically the crab pulsar. Okay, and here what is happening is basically there is a strong magnetic field, and if in the strong magnetic field, if a charged particle is gyrating, basically you get something called as synchrotron radiation, because you would have learned that an accelerated charge emit radiation, right? So this kind of emission is going to be called as a synchrotron emission. So the synchrotron spectrum will look like this. Okay, I'm not going through this thing. This spectrum depends upon magnetic field strength as well as the wavelength in which you are obtaining. And you see that it has got a negative slope. Okay. So you can see the spectrum from crab spectrum. It has got a negative slope. You can see that falls like this. And that alpha value, which I mentioned, is going to be 0.3 here. Whereas if you go to even higher frequencies, you see that the slope becomes 0.8. So this is going to be called as a spectral break, technical jargon now. Okay. And this is basically the jets from AGN, active galactic nuclei. Some of you have heard about that. This is a jet of that. This is usually seen in radio imaging. Okay. Then you have atomic hydrogen emission. Here, what is happening is basically this is actually a emission which is not seen in terrestrial condition. This is actually a forbidden line. Whenever somebody says forbidden, basically what it means is that extremely low probability of such a transition. Okay. So here what is happening is, if this is the hydrogen nucleus has got a spin. So let's imagine that the spin is in the upward direction for the nucleus, and the electron is going around it, and electron also intrinsically spins about an axis like this. Imagine something like that, though this is not a correct picture, but for our purpose it is good enough. So if the spin is aligned, that is nucleus spin and electron spins are aligned, this seems to be having slightly higher energy. So let's call that energy as E1. Other possibility is the spin could be anti-aligned. Anti-aligned means the spin may be, electron spin may be in the downward direction. So this energy is basically E2. Okay. energy corresponding to this one is E1, energy corresponding to this one is E2. There's a tiny energy difference. Okay, that is basically E1 is higher minus E2. So that energy difference is basically due to something called as hyperfine splitting. Okay, fine splitting of spectral lines. So that is from, this is your S level, S orbit, and that is splitting height finely, and it is giving rise to a small tiny energy. This transition from the higher energy corresponding to this, to lower energy corresponding to anti-aligned system. Okay, this energy difference basically gives rise to a wavelength which is going to be very close to 21 centimeter. That is why it's called as 21 centimeter line. And if you convert that into frequency, this is a very famous line. It is going to be called as 1420 megahertz line. Okay, this lies in radio. Okay. This 1420.40 megahertz lies in radio wavelength. So you can study this spectrum, and you can study the spectrum of emission. This is actually from a galaxy. I have forgotten which galaxy it is. This is a spiral galaxy. Okay. Spiral galaxy means in optical, you see this kind of a pattern. Okay. This is basically a spiral galaxy. This is the nucleus of the galaxy. And this is basically the spiral arms. So if you see a galaxy like this, some galaxy has been studied in this particular wavelength, and you see this very prominent double peak spectrum. This is a double horned spectral line. Okay. Now, why this double horn is there? Even though the emission is a very, usually forbidden lines are very sharp lines. Okay, forbidden transitions are usually give you a very sharp line. But if you look at this line, you see that it is quite a broad one. This basically happens because of Doppler effect. Okay, this is the Doppler shifted line. So if you notice this, if you take this one as the total difference is basically this end to this end is roughly about 200 kilometers. Okay, so this basically tells you that this particular spiral galaxy is approaching. This portion may be approaching, this portion may be receding. So that means the galaxy is rotating in this direction. I'm just giving you an example. So because of that, this Doppler effect happens. The spectral line gets broadened. So this galaxy, just by looking at the spectrum of this particular galaxy, you can tell that this galaxy is going to rotate about with a speed of roughly about 100 kilometers per. This is in per second. Okay, so the galaxy is actually rotating at a speed of about 100 kilometers per second. It is so. This is a very important discovery. That is to say that the spiral galaxy is rotating. This information you basically get from a radio observation. Okay, you can even image galaxies. These are actually some of my observations. This is a cluster of galaxies. It's called as HCG group, Hickson compact group of galaxies. So if you look at these one, this is a galaxy, this is a galaxy, these are galaxies belonging to this particular group. And this blue color is basically the distribution of hydrogen, atomic hydrogen. So if you look at this distribution, you see that these galaxies, though they are spiral in shape, okay, they don't seem to be having any hydrogen, whereas this galaxy has accumulated this much amount of hydrogen around it. Okay, so the question is why this happens. So this is another group, HCG group, which I studied. Here also you can see this galaxy has accumulated. The blue color is basically atomic hydrogen, H1 detected. So you see H1 is present here. Bit of H1 is present here. Hardly any H1 is there for this galaxy and this part of it. It is below the detection limit. Okay. So these are all things which you observe with radio observations. You can also do similar observation with X-ray. This is a galaxy cluster. Every point is basically a galaxy. Here is a galaxy cluster. And you see that people initially used to believe that in between galaxies there is nothing. But now if you do the observations with X-ray, you see that between the galaxy, there is matter present. Each point is basically a galaxy. Okay. Nearly about 1,000 galaxies are there in this particular cluster. But the haze is there, this blue haze. This is basically X-ray. Now, this automatically tells you that this material out here has high kinetic temperature. Okay, because it is emitting in X-ray basically means that the kinetic temperature of the material present out here should be corresponding to extremely high temperature. For example, a few keV corresponds to about, let's say, each keV is 10,000 Kelvin. Kelvin temperature. 1 keV basically corresponds to 10,000 Kelvin. You convert the temperature. So you can assume that if it is emitting in X-ray, the temperature of the intervening medium is roughly about 10,000 to 20,000 Kelvin. Okay, so you can roughly calculate what is the temperature. So question could be, what is accelerating these particles to such high kinetic temperature? Okay, so these are all interesting things for you to think about. This emission is actually due to something called as thermal bremsstrahlung, where a charged particle is getting accelerated in the electric field of a particle. Okay, that is why you get a thermal bremsstrahlung, that is braking acceleration. So what is accelerating? Where is the magnetic field coming from? Where are the particles coming from? And you will also wonder about how long had it been emitting, because the cooling time means something has to cool down, means it has to throw away the energy. So that time taken for cooling is basically proportional to square root of T divided by Ne. Ne is the number density of particles basically, and this is the temperature. So how long had it been in existence? These are all things which you can calculate from knowing the physics. Okay, so these are all interesting things to study. So you can see that. And to conclude it, particles, which I told you I studied a long time back. So air shower is quite an important phenomena. And I actually worked in this field, actually, Cherenkov telescopes, long time back. So here what happens is that particle is traveling faster than the speed of light in that medium. Okay, particle is traveling with the speed greater than speed of light in that medium. That is important, in that medium. Then basically you get the Cherenkov light. So Cherenkov light can be detected using photomultiplier tubes and things like that. So that will also give you information about what is the kind of acceleration mechanism possible. Okay, so I think my time is getting over, so I will not go into these things right now. Okay, so I'll stop here. If you have any questions, you can ask the questions now. Or if you want to go ahead, I have additional information about my work that is left to you. Since it's 1.5 hours nearly, I'll stop here basically. I thank Naxxatra, my collaborators, and all the people present here. Thank you.
Thank you so much, sir.
Yeah.
That was really informative. I actually think we can go ahead, but maybe we can take a few questions, and if we still have maybe 15 minutes time.
Okay, that is left
because we would love to hear about your work as well.
Yeah.
Okay, so if there is anyone with questions, you can unmute and ask. Maybe I'll just ask, whatever comes at the top of my head.
Yeah.
A lot of us have no engineering background when it comes to antenna theory.
Yeah.
So we see that there are a lot of different designs, right? Like
Yeah.
there is, horn antennas.
Yeah.
So
You
what
can
exactly is the foundational reason for such a diversity in design? Can you explain?
it depends upon what you actually want to detect. See, for example, the horn antenna which you saw in CMBR, cosmic microwave background radiation, that is basically to detect. Your interest is basically to study what is the absolute power which is coming out from the microwave background radiation. Okay, if you have a spiral pattern which you see, you might be trying to detect what is the polarization of the radio waves which are coming in. So you are interested in studying basically the magnetic field which may be present in the source out there. If you are interested in 21 centimeter line kind of a thing, you might basically have a detector which may be a dipole kind of a structure. So it all depends upon what is the kind of feature which you would like to study using the radio waves. That's a simple answer.
Okay, got it.
Yeah.
Okay, so would anyone like to unmute and ask any question?
Please feel free, because you guys are all youngsters. So most of you, at least, I think.
Yeah.
Yeah. So you can.
So,
Yeah.
could you tell us more about the cold spot in the cosmic microwave background?
No, I didn't get you. You want to know about
the cold spot. The cold spot.
Okay. So what you're talking about is basically, let me just, I don't have a picture for that, I think. Let me just have a look at it. 1 second. Just give me a minute. If I can go back. Okay. Okay, not this direction. If you look at this portion, what you're talking about is basically, I mean, you have better images than this, what you're seeing here. You see this kind of regions, right? In the CMBR. These could be due to, see, this is basically a temperature map, actually. Okay, so the actual original image was something like this. This is basically what you're seeing out here is basically the disk of the galaxy. Okay, so you have to subtract out all this disk and things like that. And then what you look at this region, this is basically going to be called as cold spot. Okay, and what you're measuring is basically temperature fluctuations. Sorry. So if you have a temperature fluctuations of the order of 10 to the power minus 6, I mean, just trying to recall it, I may be wrong, of the order of 10 to the power minus 6 Kelvin fluctuation, then you basically get this kind of patterns. Okay, so this kind of temperature fluctuations could be happening, and you have a cold region there. It could be due to absence of material there in this region. Okay, in comparison to the other part. So since it's a fluctuation, temperature fluctuation, it could be absence of material perhaps there. That's a simple answer.
And sir, we have a question in chat box.
Yeah.
Can you please explain in little more detail in the pattern and the direction of the array of telescopes? Okay.
So basically, let's imagine that this point is North Pole. Okay. You are in the space, you are looking down onto North Pole. So Earth is going to rotate from west to east. So it will be rotating in this direction. Okay. So if you have one telescope here and another telescope here, this telescope is going to complete one circle in 24 hours. Agreed? This will also complete in 24 hours. But suppose this is North Pole and you have a array which is shaped in the shape of a Y, like this. Okay, and Earth is rotating in this direction. Sorry, and Earth is rotating in this direction. You don't have to wait for 24 hours to complete this thing, right? This portion, once it reaches here, you have basically got this portion once it, that is this arm. If AB reaches this portion, or AC reaches this side, you are basically covered one circle, right? So instead of waiting for 24 hours, you can complete it in how much time? If you have 3 arms, in about 8 hours, you basically complete this portion, right? So you are saved on time. Okay, and this is quite important because you should understand this. If you want to use the big telescope facility, if you for example, GMRT, every 1 hour of observation which you do, Government of India is roughly spending, I'm talking about factoring in electricity bill, the salary of the people, the equipment cost, everything. If you roughly calculate it, every 1 hour of observation, basically, Government of India is spending about 8 lakhs or so. Okay, so if you want to observe for 24 hours, your single observation will fetch you, put government by how many crores, basically. You can think about that. So shorter the time period of observation with actual expenses, if you factor in, faster the observation, less cost you have to bear. Okay, so the cost versus sensitivity, that's always the question which you have. So you want to build up a telescope, you want to do it as fast as possible and with as much sensitivity as possible. Sensitivity will improve with the collection area. Okay, remember that. So you want, ideally speaking, you want to fill up everywhere with telescopes. So if you fill up everything everywhere with telescopes, then basically in a snapshot you can take the complete data. But then building up so many telescopes will cost you money, right? So it's always a compromise between these two. So that is the reason why you have the Y-shaped array.
So,
yeah.
Sir, do you think that the double slit experiment can ever be revealed as to why it happens?
This is a quantum mechanical question which you're asking me.
Yes, sir.
Yeah. See, you should. I mean, I don't know. Multiple interpretations are possible, right? Even to explain, I have even come across explanations like mini world theories and things like that to explain double slit experiment. So for me, it will be always a mystery. It is something which maybe you people can work on it.
Yes, sir. I mean, like atomic consciousness is something which is very strange. Like it's like the mother of all the weirdness.
Correct,
we do not know why it happens and how it happens.
See,
and I don't think like it has any explanation also. Like we do not look there, then there are so many lines. Like this is so strange.
So that is a fun part, right? So trying to bring in theories which are consistent with earlier observations and which will predict something. See, I can always say angels are directing the photons, right? That also could explain the double slit experiment. Okay, but then I like to explain other observations using the angels. That becomes difficult. So there is something called as Occam's razor. That means every theory, the least number of variables you should have. So you choose a theory, if multiple theories are possible to explain the phenomena, you choose the theory which has got the least number of variables. That is Occam's razor. Science works on that principle. Okay.
And so what would you say about the string theory?
I don't know much about it. I cannot comment on it.
All right, sir.
So we have another.
Yeah. Go ahead, Sagar.
We have another question, sir.
Yeah.
Sir, we know that radio interferometry is widely used in astronomy.
Yeah.
What goes into building them? And is optical interferometry feasible given that the surface error required is very less?
See, optical interferometry is in the beginning stages. Actually, people have started doing it, optical interferometry, because you can have high precision movement, but not at the size of GMRT or something like that. Okay. For example, you might have heard about the Gemini telescope facility, which is about 10-meter optical telescopes, if I remember correctly. I mean, I don't work in optical, so I take all these values with a pinch of salt. Okay. There they have managed to do interferometry, optical interferometry. But if you are asking a question whether an imaging is possible using an optical interferometer, that will take a lot more time. It's a much more challenging task. Okay. But it's possible. In principle, it is possible, because our electronic systems are becoming much better.
Good afternoon, sir.
Yeah.
Sir, I am basically studying electronics and I'm in 6th semester.
Yeah.
So I want to pursue my career in astrophysics and I aspire to be an astrophysicist.
Okay.
So, but then I am not understanding how to go about with research and how to choose a domain and things like that. So if you could just, throw some light on how undergrad students can, get into the field of research, that would be very helpful for me.
Okay. So you believe that your first thing you have to understand is when you have to think about is what are your strengths. Okay. So since you said that you are an electronics student, I presume that your strength may be electronics, right? So if that's the case, you should definitely do a master's in either physics or in electronics, and then you should try to get into research. Okay. Now, always build your research career on your strengths, because if you are not very good at mathematics, if you aspire to become a theoretical physicist, then you are actually you will actually give up, actually, to be very honest with you. Whereas, see, I personally, I realized it quite late that I am okay as a data analyst or as an observer, but I'm not very good at theory. Okay. So my strength is precisely that. So that's the reason why I've decided to become an observational astronomer. If your strength is in electronics, maybe you should think about building up instrument, which will, so you go into instrumentation, basically, if your strength is that. Okay. So you have to be fairly aware of what are your strengths and then build up on that. That is my suggestion in this case. Instrumentation is quite an interesting task. For example, building a new telescope, new design of a telescope. Somebody asked a question about different type of telescope, right? So why not have a telescope antenna, which may not be even spiral or a dipole antenna. You could have a different design which might reveal a different feature about the celestial object. So you should think about that, perhaps.
Yes, thank you, sir. That was really helpful.
Sir, we have another question.
Yeah.
Could you please explain how particles travel faster than light in that Cherenkov radiation?
Okay. This is like a shock wave. Okay. See, you have all seen, I presume that you have all seen, okay, the refractive index, if you look at the definition of refractive index, is basically speed of light divided by speed of light in that medium, right? This is basically refractive index of a medium. Am I right?
Yes, sir. Yes.
So in a medium, light could have a speed which is different from speed of light in vacuum. Okay, so exactly the same way, if you have a plane traveling in air with Mach 1 or Mach 2 speed, you basically have seen this shock wave, right, which looks like something like a cone. Some of you would have seen that kind of a feature. So exactly the same phenomena happens in the case of light. So this cone, which you see in the case of light, when a particle is traveling at the speed which is greater than the speed of light in that medium, then you will get a shock. That shock is basically the Sharon-Role radiation. Okay, I'm not drawing the diagram and trying to derive it to you. You can actually look it up in many of the textbooks.
Sir, can I ask?
Yeah, please.
Sir, what is the royalty fee like when it comes to when you're giving up, when you're handing over a research to an organization? They say that they'll pay in royalty fee. What is royalty fee?
Yeah. Any kind of observation in an observatory, it's a competitive proposal, in the sense like you're asking me about that, right?
Sir, royalty fee, sir. Yes, sir.
Okay. So astronomers generally don't charge you to use the telescope facility. Okay. Usually the government pays for that money in most of the countries. But your proposal, when you want to observe with a telescope, your proposal has to be so solid or something which nobody else has done before, or improving on somebody else's observation. Then only they'll give you time to do with observation with an observatory. Okay, it's a competitive thing. If you have to use GMRT, or if you have to use VLA or WSRT, you have to say the reason why you want to do that observation. Okay, and what is the expected outcome of that observation. So based on that competitive, there'll be a team of scientists who evaluates the quality of your proposal. And if your proposal is pretty good, they'll say, okay, you come and observe with our telescope facility. It is free of charge. Okay.
Yes,
so
sir.
You don't have to pay any money.
Okay, it's because actually the research what I'm doing is not interdisciplinary.
What are you doing? If you don't mind me answering.
Sir, it's very rarely, it's very few done by everyone. Like, especially I'm saying that when the whole country, it's like not everyone does it.
Okay.
A few does it, like rare. Defense. Sir.
Yeah. So that is fine. There is no problem. Nobody. See, scientists are capable of assessing the merit of your proposal. So you have to just put in that request. I'm not talking about defense facilities. Defense facilities, I have never given a proposal. I don't know. Whereas astronomical observatories, you can always give a proposal. That proposal should tell what is the kind of observations you're planning to carry out, what is the outcome, expected outcome. You may not succeed in getting that outcome. That is okay. But you have to mention about what is the expected outcome. You have to mention in which, because of that expected outcome, what is the growth in astronomy which is going to happen. So these are all things which you have to explain to the committee who will review your proposal.
Sir, do you have any idea where we can get carbon metals, sir?
Sir, do we have time constraints? So can you proceed to the next question, sir?
Yeah. I can go ahead. I'm left to the moderator.
So what are your thoughts on segmented telescope? Are they better than conventional telescope?
See, segmented telescopes are usually used in optical astronomy. Okay, so what you're doing is basically you're trying to see, the biggest challenge in building a big telescope is, like, for example, you have the 30-meter telescope which is coming up. Okay, so if you want to have a telescope of that size, mechanical support is required, and the mirror will actually flex if you don't support it properly. So instead of having a 30-meter telescope, a single dish, you actually make it in the form of honeycombs and then build up the structure. So it is again a compromise between cost, the accuracy which you require, etc., etc. Okay. So they are building it up. 30-meter telescope, they are coming. India is part of it. Segment telescope.
Okay, sir. And sir, can you, if you don't mind, can you give about your work, tell about your work in 2-3 minutes before you conclude?
All right. Maybe I'll just show you those images. The last part of my. Okay. So what I had done is basically I have imaged galaxies like this. Okay. I showed you the images, some of the images of this. Now, the question is basically why this kind of behavior is seen. This is due to something called as, it could be interaction. So you can have hydrogen getting pulled out of a galaxy. Okay. So you can see here, this is a very classic picture. You see this is a picture of the galaxy taken in optical on the left side. And you see that the same image is taken in 21 centimeter atomic hydrogen. So you can actually see material getting pulled out from one galaxy to the other. So this is a clear-cut indication of interaction. Okay. So what I did is basically I imaged galaxies. Then I did a Fourier analysis on the galaxies. Okay. Fourier analysis means like if the distribution of matter is like this, I extract out the atomic hydrogen in concentric circles. Okay. So in some region, there could be high density, some region there could be low density, and so on. So you open up these rings and then Fourier analyze them. And then you determine what is the Fourier coefficients. So these are basically the normalized Fourier coefficients, what you see here. And this is basically distance from the center of the galaxy outward. Okay. So you see this kind of a distribution in the atomic hydrogen. That means as you go more and more outward, the asymmetry increases. Okay. So I was able to quantify how much is this asymmetry. I was the first person in the world to do this for atomic hydrogen. Okay. So as you go outward, the asymmetry seems to be increasing. Now the question is, what could be the reason for this asymmetry? So for that, what you do is basically you compare it with optical asymmetry and so on. And then you see that you can even model it. Model it means basically, I didn't explain all those things. Okay. So what happens is that this is actually from my own observation. So you get the velocity information. You also know the velocity, distribution of matter around it. From that, you can find out how much is the asymmetry in something called as the dark matter halo potential. So this is what the asymmetry in the dark matter halo potential, which I could detect. Okay, using that Fourier coefficients. So I just gave you a simplified explanation about what I did. You heard about dark matter, right? Many of you would have heard about dark matter. So the idea is basically the galaxy, visible galaxy may be embedded in, this will be the visible galaxy. Okay. So the visible galaxy is embedded in something called as the dark matter halo. So dark matter interacts with visible matter. So I have the visible matter, which is basically in atomic hydrogen. Why atomic hydrogen? Because you've seen that if you look at this diagram itself, the visible size of the galaxy is only this much. But atomic hydrogen extends all the way up to this much. Okay. So I'm able to study the perturbation on the matter due to dark matter. So that is what you're seeing here. This is the distance of the galaxy from the center outward. The optical size will be of the galaxy is only this much. Okay, roughly about this distance. This is 3 kpc, kiloparsec. In normalized units. Okay. But in H1, it is extending all the way outward. So when it's extending all the way outward, if you observe this kind of perturbation, how much should be the perturbation in the dark matter potential? That is what I studied. Did you understand something at least?
Yes, sir. We actually have a couple of groups in Naxxatra who are working on some dark matter related projects.
Okay.
I think this would be really interesting to know more. Is there any kind of resource or document you could send us in case it is not confidential?
No, it is not.
That-
You can always see this my papers there on the web.
Okay.
It's available on the web. You can
Okay.
search. You can go to this ABS.
PDF. Okay.
ABS. It's called as Astronomical Data System. Okay, so you Google search for this ABS, and you'll get a form. There you can put in my name. Okay, Angiras.
Okay.
So you will see a few of these papers. You can download freely.
Okay, sir.
Check it out. Okay.
Okay, so I think we can conclude. We've taken a lot of your time.
Yeah,
as
no
well.
problem. No problem. Absolutely no problem.
Thank you so
Okay.
much. That
Okay.
was one of the best talks we've had in a long time. So just thank you so much for all the information.
Thank you for calling me.
Yeah.
Thanks, everyone. Bye.
Thank you. Bye. For others who are on the call, we are going to be starting our next session for deep sky objects through the perspective of an amateur astronomer. And that talk is going to be given by Akash Sinha, who has a PhD in physics from the University of Texas. He's currently in the US, but is in India right now for a short visit. And he was kind enough to give a talk today, and he has put together a really, really interesting presentation about all his experiences in stargazing and astrophotography. So he has been doing this for more than 10 years now, and he has some amazing experiences. So those of you who have any plans for observation sessions at all, or if you ever plan to, go into amateur astronomy, or even just look at it as a hobby for the future, then you really have to attend this talk. So just hold on, and I would suggest that you stay on the call because we're starting in 5-6 minutes now. And yes, so those of you who have not had your dinner, I mean, we know this has been a long session starting from all the way from 6:30. So I don't know, feel free to have your dinner while attending the session as well.
Hi, am I connected and audible?
Hello. Yeah, hi. Yeah, you're audible.
Okay, cool. Thank you.
Yeah, so we'll just wait for 10 minutes because the previous session just ended.
Okay. Yeah, it's also like 5 minutes early now, so.
Yeah.
What about the presentation? Is that visible now?
Yeah, I can see.
Okay, cool.
Yeah, so before we begin, I just want to say that this recording will be there on YouTube. We are streaming this, so the link is put up as well. So you can find the entire evening session on YouTube. So I think we can just get started. So first of all, thanks a lot, Akash, for joining us today. Akash has been interested in astronomy as a hobby for the last 15 years, since his 10th standard days. He used to be a regular attendee of ABAA, which is in Bangalore, and one of the early members of Bangalore Astronomical Society. I'm sure a lot of you would have heard of BAS here. He holds a PhD in physics from the University of Texas and now works as a software engineer in California. His primary interest in astronomy is in the visual astronomy of the deep sky, although he dabbles in astrophotography and DIY projects. So, yeah, he's had more than 15 years of experience in visual deep sky observations. So, I think it's a very rare treat for all of us to listen to someone like him, because we don't easily get access to people like this who are pursuing their passion for so many years. And also, we are interested, Akash, if you can tell us a little bit more about how you got started in amateur astronomy and why you decided to keep pursuing it for so many years. That would also be really a source of inspiration for all of us here. So, yeah, without much delay, let's get started.
Okay. Thank you, Sitara, both for creating this platform and also for that introduction. Since you, I just want to double check that I'm audible, right?
Yeah.
Okay, perfect. Since you asked, let me tell you about my background in amateur astronomy before I get into this. So I I think I was a computer nerd before I started astronomy. So initially, I thought astronomy was very boring because it involved memorizing the properties of planets and such things. The 10th standard syllabus back then had a chapter on astronomy, which was around the same time when I happened to find. I used to be interested in Linux back then, and so I installed Linux and I found this app called K-Stars, and so a lot of things came together at the same time, both the 10th standard chapter on astronomy and finding this app, and and what I used to do is try and map out the constellation pictures that I saw on the app with the sky. I used to run up to the terrace and back to my computer trying to do this. And I also found some books that my parents had bought me on astronomy with all of these beautiful pictures. And I really hope to see these things someday. Uh, and somewhat serendipitously at the same time, I had just finished 10th. I then learned that my school was going to build a telescope, some of the students in my school. And I got very curious. I had just left the school then. I had gone to PUC. I studied in state board. Um, uh, so I got very curious and I tried to find out where these folks were going. And that's how I found ABAA, Association of Bangalore Amateur Astronomers. And I started going every Sunday to Abba, and I built my telescope there, my first telescope. And that's where the passion really hit me. One of the senior Abba members kind of challenged me, now that you've built a telescope, why don't you see all the 110 Messier objects? These are deep sky objects, and I'll of course describe what deep sky objects are. So I took that up as a challenge to do within a year, and that's how I got sucked into this field. So this happened around 2005, and so ever since I have graduated to bigger telescopes and harder challenges, and now I'm also starting to learn what I'm looking at, and this presentation is all about that. Trying to also explain the science behind whatever I observe. Okay, so let me perhaps get started. Um, um, so this talk is on deep sky objects from the perspective of a hobby astronomer. So I should clarify that I'm purely interested in astronomy as a hobby at present, and I have no formal background in it. but this is my attempt at learning some of the science behind what I can observe. So before we begin, let me introduce amateur astronomy. So who is an amateur astronomer? An amateur astronomer is somebody who does astronomy as a hobby. It doesn't mean that they don't know anything about astronomy. It mostly means that they do it as a hobby. They don't have formal training in astronomy. Some professional astronomers also do amateur things for fun, but most of us don't have formal training. And we don't get paid to do astronomy. This is our hobby. And the aim of most amateur astronomers is to have fun and not necessarily contribute to science. And some amateur astronomers, of course, do contribute to science, but most of us are interested in popularizing science or just there for fun, because we want to enjoy science. So why do it? Like I said, one of the top reasons is enjoyment, and specifically intellectual enjoyment. So the famous physicist Richard Feynman, you might have heard this term intellectual enjoyment from him. And his point was that there is a lot of joy in thinking about the universe and trying to understand it. And in some sense, a lot of us amateur astronomers do it for that reason. Then there is aesthetics. The universe is really beautiful, beautiful nebulae, beautiful galaxies. And it's a joy to look at these things and also photograph them. And for many people, it's about building things, building astronomical instruments. So many people make their own telescopes, grind their own mirrors, and the joy that they get when they build that telescope and look through it, that is also a reason why they do it, because they like building things. And especially for younger people, amateur astronomy is a source of inspiration. So many people who have started out as hobbyists have taken up, especially in their high school days, have later gone on to become professional astronomers or professional physicists or any of the related science fields. And then there is education and outreach. Amateur astronomy is a big tool in inculcating a scientific spirit in people. So when we show them Saturn's rings through a telescope, we get a lot of questions. Does this cause us? Does Shani cause me harm, and so on and so forth? So it's a tool to try and spread science and inspiration towards science to others. And another reason is friendships. You really meet a lot of cool people with interesting interests in an amateur astronomy club. For example, many of the people that were ABBA members also were into ham radio and hiking and so on. And so usually you will have an intermingling of hobbies, and you will have a lot of things to learn from these people, and also fosters friendships. And there's one reason that I don't list here, and it's a sort of a strange reason, if I may. It's astronomy is sort of a spiritual science, if you ask me. You end up asking the questions of what is the purpose of this universe, what is, who are we, why are we here, kind of things. And whether we can answer those questions or not, astronomy, for some people at least, provides an inspiration to think about these things. So that's amateur astronomy in a nutshell. And this talk is about deep sky objects. And what is a deep sky object? It is something it's a celestial object that is outside our solar system. So things like planets, comets, and asteroids are not deep sky objects. But things like nebulae and galaxies, which are outside our solar system, are deep sky objects. Even clusters of stars. Individual stars, even though they are outside the solar system, are seldom called deep sky objects because we want things to be more interesting than individual stars. So that's the definition of a deep sky object. And the purpose of this talk is to introduce the beautiful types of deep sky objects that are there in our universe. And it's all from a visual observer's perspective, although I will show you a lot of photographs taken by hobbyists. And what this talk is not, it's not an introduction to techniques of deep sky observing. I already recorded a 4-part talk series on this, going very deep into the techniques and methodologies of deep sky observing, including averted vision and all of those things that you may have heard of, how to look through a telescope, basically. So I want to put that away, and there's already a talk series on that. But so this one is focused on introducing the kinds of objects that exist and sharing observations and photographs of them by friends. Okay. So the aim of this talk is to inspire others into deep sky observing and photography. Okay, so let's now do the following exercise. Let's pretend that you had no scientific background in astronomy and you just went out and observed the night sky, like our predecessor astronomers, all the way from Ptolemy to Herschel and all of them did, right? So suppose you just go out in a dark site under a clear moonless night, and then you look at the night sky. Then you'll see stars, and you might identify patterns that are the constellations. Like here is a picture of Orion. For a moment, ignore the fuzzy red patches, the nebulosity in this, and just let's take the brightest stars. So you won't be able to see these many faint stars with your naked eye, but you will see these 8 or 9 bright stars that are in this constellation, and you can join them by imaginary lines to create the shape of the hunter, Orion in this case. So that's one thing that you will observe, stars and their patterns. And you might also notice that the stars have different colors. For example, the star on the top left here, I don't know if you can see my mouse cursor, but I'll highlight it. So that star is distinctly red, and if you go out and look at Orion, you will actually see that the star is red with your own eyes. Okay, so these are the two things you might observe. And if you're in a really dark site, you will be able to also see this cloudy band that we call the Milky Way. That's our own galaxy, right? And if you look carefully at the Milky Way, it is full of these patches of light. It looks like clouds, basically. And in between those patches of light, there are dark rifts. So these are the dark structures, like here. And so you see these dark structures protruding through the bright clouds. And you may also, if you have sharp eyes, dark sight, and good technique, then you might see fuzzy patches called nebulae in addition to the Milky Way. So I've highlighted 2 such nebulae in this photograph. They are going to be hard to see, and usually you will need a technique called averted vision, but you can see these patches. They're just fuzzy patches. And if you were observing in the days of Ptolemy or Charles Messier or whatever, you would not know what these patches are other than that they are patches. So now let's suppose that you got a small binocular, even a simple binocular like this that you can get for about 3,000 rupees can show you a lot more than the naked eye can. And so let's say you went out in the night sky with this binocular and looked at some of those fuzzy patches. Then some of them will start looking like clusters of stars, and others will still look like fuzzy patches that don't resolve into anything. But some of them will resolve into clusters of stars like this one. This one's called beehive cluster. It's what we call an open cluster of stars. It's a group of stars which are well separated, and we will later learn that these stars were kind of born together. They have shared history. Now, seeing much more, you might see some structure in some of the fuzzy patches with a binocular, but seeing much more, you would benefit from having a telescope. So here's a picture of my first telescope, which was made at ABAA. It's an 8-inch mirror reflecting telescope. So if you look through a telescope like this, some of those patches will clearly look like patches of gas, which are called as gas nebulae. So just to clarify, nebula is a generic term. It just means cloud. But usually when we say nebula, we usually are referring to a cloud of gas that is usually glowing or reflecting light or something like that, that we can see. So here's a picture of a gas nebula. This one's called Orion Nebula. So this is pretty close. This is a picture, but this is pretty close to the view that you would see if you point at the telescope that I showed you earlier at this object. Some of those fuzzy patches will start looking like this. These are called globular clusters. These are clusters of million, that is like 10 lakh or more stars that are very close by. This one's called Omega Centauri. So if you used an 8-inch telescope, in some of these globular clusters, you might start seeing that they are composed of stars rather than just as a fuzzy patch. So that's how you know that some of these fuzzy patches are actually made up of stars and some of them are actually made of gas. And then you can also see galaxies, but people who are just looking at the night sky had no clue what these are. They just call them spiral nebulae and such things. So here's an example of the spiral nebula in Canis Venatici or whatever, right? Canis Venatici is the name of a constellation in which it exists. So these were called spiral nebulae earlier. They were just thought to be a different kind of nebula, but today we know that they are galaxies. So on the left here is a picture taken by one of our BAS members, Kirti, and on the right is a sketch by American amateur astronomer Howard Banich with an 8-inch telescope. So you have to rotate this sketch kind of this way to make it match the image. So this smaller thing corresponds to this thing. The rest of the sketches I've tried to rotate so that they match the image that I'm showing. So if you look through an 8-inch telescope, you might see something like this. You might not see all the spiral structure, but you can see some hints of it. This is what you can see with the telescope. And this is probably all that people did in the days of William Herschel. People cataloged these kinds of objects, but they didn't really know what they were other than, okay, they knew that there are star clusters when they could see those, but the nebulae, I guess this was the amount of understanding people had. So now let's talk about what modern astronomy tells us about what we observe. So now I'm going to draw on our current understanding of the universe to show you how we can see the various aspects of stellar evolution and so on in the night sky, and how to relate what you observe to the science that we know. Okay, so first let's talk about stars and constellations. I think most of you know this already, that constellations are imaginary. They are, our brain likes to see patterns even where none exists. For example, this star called Bellatrix in the constellation of Orion is much closer to us. See, it's only 250 light years away, whereas the others are much further away from us. So if you looked at Orion from a different vantage point other than the solar system, suppose you could imaginarily travel to a different star, then the shape of Orion would look very different because these things are actually in different distances in 3D. The other thing is, remember we said that we see colors in stars. Modern astronomy tells us that the color is related to the surface temperature of the star. Those of you who attended previous talk probably remember something about black body radiation and Wien's displacement law. So the same idea here, blue stars are hotter than red stars, and yellow stars are somewhere in between. So the star colors that we saw are related to their surface temperature. Okay, so now let's talk about how stars are formed and how stars die, and how we can see various parts of this process and enjoy them. Now, I must apologize. A lot of the sketches that I show you are with very big telescopes, but even with a small 8-inch telescope, you might not see as much structure, but you will certainly see the object. So you can learn about the object and relate to it by actually observing it. I will show you very few of my own sketches because I'm not very good at sketching. So most of my sketches come from Howard Banich and Uwe Glan, two people whose pictures I'll show you at the end. So when William Herschel looked at the Milky Way, he saw such dark patches, which he thought were holes in the heavens. Okay, these are patches that are devoid of stars. So he thought there were no stars in those regions, and there were sort of holes in the sky that is otherwise full of stars. But today we know that these are actually dark clouds of dust and gas. This one's called Barnard 68. It's just a catalog designation, as we call it. So because there are too many deep sky objects, you don't give them all names. Instead, there are catalogs and there are numbers associated with those catalogs. So Barnard was a famous American astronomer who cataloged dark nebulae, amongst other things. So this is a dark cloud of cold gas and dust. And this is where modern astronomy tells us stars actually form. So here's another example of a dark cloud that is really well known. It's called Horsehead Nebula. The Horsehead Nebula part is just this tiny black thing. I don't know if the resolution of the webcast shows it clearly, but I'll show you a bigger picture in a moment. But it's this black notch that is protruding into this red background. And we are able to see it even though it is dark because it is blocking the light from the red background. So the red is actually glowing gas, and this cold gas is jutting, gas and dust is jutting in front of it and blocking the light, so we are able to tell it. So on the left is a picture, and on the right is a sketch that Howard Banich, American astronomer, amateur astronomer, has done with his own eye at the eyepiece. So that is his own sketch of what he saw in the eyepiece. This is what Horsehead Nebula looks like if imaged through a very big telescope. That's why it's called the horsehead, because it sort of looks like a horsehead. It's just a dark cloud of dark molecular gas. Cold molecular gas. So that's where stars form. In addition, we see these dark nebulae in the background or in the presence of bright nebulae like these globules that are called Bok globules. What this is it's actually these two things here are actually dark nebulae that are wrapped in a shell of in a shell of glowing gas. Inside that glowing gas is dark a cold molecular cloud where stars are forming. Like I said, we are able to identify these dark clouds because they are wrapped in glowing gas. So there we identified them because they were blocking the background light. Here they're sort of wrapped in glowing gas. These can also be observed visually if you have a good technique and a good telescope. Here's an image of the same. I mean, this is a crop from a wide field image by Shubhankar Saha, who is a Bangalore amateur astronomer. And he has those tadpoles that as we call it, the Bok globules. And here's a sketch of the same by German amateur astronomer Uwe Glan. And here's my very rough sketch. So you can see these things. This particular one is extremely hard to see, but it can be done. So protostars, which are early versions of stars, form in these Bok globules, but we can't see them. We cannot see them because they are blocked by the dark nebula, and they also emit mostly in infrared, which we cannot see, obviously. So you have to use an infrared telescope to see these things or image these things. It's not possible to see some of these protostars visually, but we can see that they exist by looking for something else. So when a protostar forms, there's a disk of material that is falling into the protostar and accumulating to form the star. What this is it's essentially condensation from the gas around it. So the gas cloud is collapsing to make a star. And it forms this accretion disk. And because of various magnetic field related things, it also throws out material in this direction, the polar jets that are marked in this image. What happens then is that this polar jet of mass that is coming out of the star, that is being thrown out of the star along its poles, goes and hits the cloud that is surrounding it and causes it to glow. Then you get something called a Herbig-Aaro object. It's named after two astronomers who found this and studied this. So you can see this. Even if you can't see the protostar, you can see these Herbig-Aaro objects. And here's an example. On the left is a picture from a professional telescope. It's called the Digitized Sky Survey. And the part that I've highlighted here, the two blobs of light here, are the Herbig-Aaro objects. And here's a sketch by the same German amateur astronomer Uwe Glan, who has sketched these two. They're very faint, and they're on my list of things to see. I've not managed to see them until now. They're pretty challenging. This, by the way, is just a what we call a reflection nebula. I'll get to it in a moment. Okay, so let's say the star finishes forming. It's no longer a protostar, but a young star. Then what you're seeing here is that light is reflecting from the young star on this gas. And we are able to see the light that is reflected, or more precisely scattered by the gas that is behind the star or near the star. So this kind of nebula is called reflection nebula because it reflects the light of the star. Okay, so here's a different reflection nebula that is near a young star. And what happens with young stars is that they are unstable, so they throw out matter as they are forming or as they are becoming stable. They throw out matter, and this matter comes and blocks the light of the star falling on the nebula. So the brightness of the nebula actually changes because of the clouds of matter ejected by this young star. And so you get these things called variable nebulae. So this example is called Heinz variable nebula. And this is a photograph by, I think, a semi-professional astronomer, if I may say, call him that, Adam Block. There is another such nebula called Hubble's variable nebula, named after Edwin Hubble. And it's the same concept. There are clouds ejected by the star, and that the shadows of that change the appearance of the nebula. And here's a series of sketches by Howard Banach with his 28-inch telescope. I had the eyepiece, pencil sketches, and he has cataloged the variation of this nebula over time. So, this is a sketch. I'm about to switch to a video by Tom Polakis, another amateur astronomer who has taken photographs of this nebula and created an animation. So let me be back momentarily. So do you see this video? So here, the video you're seeing shows the shadow of the mass ejected by the clouds ejected by the star on the background reflection nebula. So you can see that those clouds are moving, and therefore by virtue of the shadows that are moving. And fun fact is that if you try to measure the speed of the shadow, it is faster than light. And that's how you know it's a shadow, because shadows are allowed to travel faster than light. It's not a violation of special relativity. So now let me get back to the presentation. So I just want to highlight that work was done by an amateur astronomer in Arizona in the US. We talked about young stars. The other thing is stars form in clusters. The same molecular cloud, the same dark nebula, collapses and forms many stars together. And that's why you get stars in clusters. And those clusters are called open clusters. Here's a picture of the open cluster NGC 2244 by Kirti Kiran of BAS. And it is surrounded by some nebula, but let's not focus on the nebula right now and just focus on the cluster of stars. So all of these stars are roughly, are born out of the same molecular cloud, and so are roughly at the same distance from us. So here's another example. This is a much older cluster. This is called NGC 2477, and this photograph is by Shubhankar. Okay, so as you saw in the previous picture by Kirti, so sometimes what happens is that the light from the stars in the clusters, especially the hottest stars, the most luminous stars, the light from those stars comes out in ultraviolet, and it ionizes the gas. So it strips the electrons off the atom, and so it becomes hydrogen. Hydrogen gas becomes protons and electrons. Right, and then when the hydrogen recaptures that electron, the proton recaptures the electron to form hydrogen again, then it emits light. And you know this, you might have studied in physics or chemistry, this Lyman series, Balmer series, and so on. And what we are seeing are the Balmer emissions, because those are in optical. And that's what this pink light is. This pink light is coming from hydrogen gas that has been ionized and is recombining. This blue light here is a reflection nebula. So that's sort of not from glowing gas. Whereas this pink gas is actually glowing. And what causes it to glow is ionization from ultraviolet light from the cluster stars, the bright stars that are forming. And this one's called Trifid Nebula. On the left is a picture that I took many years ago. And on the right is a sketch by Howard Banach again with his 28-inch. These are called emission nebulae, or H2 regions sometimes. And here's a picture in grayscale by Kirti of another such nebula called Eta Carina Nebula. And what he has done is he has used a filter that only allows the light from glowing hydrogen of a specific wavelength. And he's made this image with the H alpha filter. So you can see the structures, and you should imagine in your head that most of this is pink colored. Okay, so as these stars form from the gas and you form these beautiful nebulae by ionizing the radiation and so on, the stars enter what's called the main sequence. Perhaps you've studied about this already. It's a form of stable star where, like our sun, where it emits radiation and burns hydrogen into helium through nuclear fusion. So stars enter this main sequence, and you can think of it as the midlife of stars. And then they enter their old age in the form of red giants. So the star on the top left of this picture called Betelgeuse in Orion, this red star is a red giant. It's sort of a star that is going to die sometime soon. So depending on the mass of the star that it started out with, its destiny when it dies is different. So if a star is about less than 8 times the mass of the sun, then this is how it ends up. So when it becomes red giant, and then what happens is that the red giant has an explosion of its outer shell, and the inside core becomes a white dwarf. And this outer shell becomes what's called a planetary nebula. So it forms these beautiful symmetric patterns in the sky that we can observe. On the left is a photograph of this so-called ring nebula. This is a photograph that I took with my telescope. And on the right side is a sketch by Howard Banach again with his 28-inch telescope. And you can see that colors are very hard to discern with your eye. This is one of the few objects where if you try really hard, you can see some color. So that's why most of the sketches are grayscale. The pictures can be colored. But yeah, the sketch here is grayscale. So the star that is in the center of this is a white dwarf. That's the remnant of the core of that red giant. Okay, so this is what happens to low mass stars. Here's another example of a low mass star after it has died, so to speak. This one's called NGC 2392. On the left is a picture taken by Hemant Haryani, founder, president of BAS, and he's now in Texas. So he's taken this picture with a 16-inch telescope. And here's a very rough sketch of that I made at the eyepiece of a 48-inch telescope. Okay, what about high mass stars? Stars that are more than 8 solar masses, they explode in violent explosions called supernovae. They are some of the most violent some of the most violent energetic events in the universe. Even though there are more energetic things, these are some of the more energetic ones. So a supernova in our galaxy probably last occurred sometime in the 1600s. There have been records of supernovae all the way from 1054 AD when Chinese astronomers observed a supernova and so on. But we are sort of overdue for a supernova in our own galaxy. It's been about 400 years and we haven't had one. So hopefully it'll happen in our lifetimes. People say that when this happens, it is so bright that you can see the exploded star in daylight, even though it's many, many hundreds of light years away from us. And but even though in the last 400 years we haven't seen a supernova in our own galaxy, we have seen supernovae in many other galaxies. Here's an example of a supernova in a galaxy called the Cigar galaxy, or M82. It basically looks like a star. You would not know unless you notice that it's a new star on a galaxy, unless you knew the star patterns, you would not know that it's a supernova. It just looks like a star. But the beauty of this object is that it's actually in a different galaxy and we are still able to see it. It's an exploded star in a different galaxy. It is so bright that we can see it. And sometimes it outshines the entire galaxy. So the brightness of the supernova will be will be higher than the core of the galaxy that it's part of. So here's a picture before and after. Here's my sketch of a supernova in a galaxy called M61. This was last year, and so you can see it's called SN 2020 JFO. So it was in the year 2020. So sometime last May or something like that, supernova happened in this galaxy, and I took a look at it. And this is my sketch. And like I said, I would not know that it's a supernova. In fact, I probably came back home and looked at the picture of M61 that was taken before the supernova and identified this particular star, saying, okay, this is the supernova, right? The other things that I marked here are the spiral arms and nebulae in the galaxy, basically, in the sketch. So after the supernova happens, the exploding star basically sends a shock wave through the interstellar medium, basically the gas and dust that clouds that pervade space. And then some of it ionizes and so on, and you see these nebulae that are called supernova remnants. So a supernova remnant will usually have these filamentary structures, like you see these filaments here. These are because of shock waves coming from the nebula, from the supernova, from the exploding star. And so on the left is a picture by Prabhu Kuti, who lives in the UAE, of Crab Nebula, this particular nebula. And on the right is a sketch by Howard Banich with his 28-inch telescope. So this is the nebula formed by a dying high-mass star called a supernova remnant. Okay, so that's the summary of stellar evolution processes that happens in our galaxy, and we can see a lot of this. I'll take a momentary pause here for like maybe 2 or 3 minutes to answer some of your questions. Are there any questions?
Are you going to be addressing the kind of equipment you use to capture the images that you've shown us so far?
Not in this talk.
Okay.
I might show you some pictures towards the end, but in this talk, I won't address that, unfortunately. But the thing is, BAS has put together a lot of practical videos on this. And if you go to BAS's YouTube channel, you'll find a lot of videos on equipment and techniques and so on. Okay, let me proceed. I'll do one more question session at the end.
We got some questions.
Oh, okay, sure. Go ahead.
How is NASA still in contact with Voyager 2?
I wish I could answer that question, but I don't really know. They must have good transponders. That's all I can say. So I'm not an expert. I would not know the answer to that.
Okay, and there's another question. Is it possible to observe any deep sky objects with a 3-inch reflector telescope?
Absolutely. The answer is yes. You can observe lots of deep sky objects with a 3-inch reflector telescope. What you need is proper technique and dark skies, moonless, clear, away from the city. and and good pointing technique. You will need to know how to find these objects. uh, this is one of the reasons we recommend binoculars for beginners over telescopes, because telescopes are a little harder to maneuver. They have inverted image and they are on a mount. You have to move them and you have to know how to correctly move them, and follow a method called star hopping and so on. But yes, it's definitely possible to observe deep sky objects with a 3-inch telescope. It just takes effort and a little bit of technique. Okay,
I,
so let me proceed. Um, so now we talked about everything inside the Milky Way. So let's talk about outside the Milky Way and seeing stuff outside the Milky Way. This is one of my favorite aspects of deep sky observing. This is probably the thing I'm most passionate about, and that's galaxies. So, like I said earlier, when people like William Herschel looked at galaxies, they did not know that they were outside our Milky Way. Even the notion of Milky Way was probably not very clear. Um, in fact, in the early 1900s, there was a heated debate between two astronomers, Shapley and Curtis, on whether these objects are outside the Milky Way or inside the Milky Way, as these spiral nebulae and such things. And Edwin Hubble kind of settled this with this famous photograph. I learned this fact from Kirti recently. Uh, and This famous photograph has, also called the VAR photograph. What Hubble did is he detected a certain kind of variable star. So this is a star whose brightness changes with time in a well-defined manner. And if you observe the changing brightness of the star, you can actually find out how far it is. And so by that, he was able to find out that the star was more than 1 million light years away from us. And based on that, he recognized that the thing that the star was part of, this nebula that the star was part of, actually was outside our Milky Way. And so he basically settled this Shapley-Curtis debate, and that's how. And then we learned that there are island universes outside the Milky Way, and we now call them galaxies. So that was the discovery of galaxies in the 1900s. And the other mind-blowing thing is people pointed the Hubble Space Telescope to what they thought was an empty patch of the sky and took a very, very, very long exposure photograph, and they found that it was full of galaxies. So almost every dot in this picture is a galaxy, uh, many billions of light years away, right? And basically the universe is full of these galaxies. So there are broadly 4 types of galaxies based on their visual appearance. On the leftmost is what you probably think of when you think of a galaxy. It's a spiral galaxy, and it has this spiral structure with spiral arms and so on. A spiral galaxy is pretty much flat with the bulge in the center. You can think of it like a dosa or a pancake, and the topping on the pancake or the potato filling on the dosa is kind of the central bulge. And just like, I guess dosa is a better analogy. So just like when you make a dosa, they make the spiral pattern, you have the spiral arms. So it's pretty much flat except for a bulge in the center. And I mean, relatively flat, right? I don't mean that it's really thin. I don't know how thick it is, but it's many, many, many light years thick, right? But the thickness is much smaller than the size, the radius of the galaxy. Um, so that's a spiral galaxy on the leftmost. On the center left is a barred spiral. It's pretty much a spiral, but in addition, it has this bar going up and down in this picture. So those are barred spirals. And then there are irregular galaxies like this one here, that's called Barnard's galaxy. These have no structure or pattern as far as we can tell. And on the right here is an elliptical galaxy. For a moment, ignore that blue thing coming out of the center. That's a jet from a supermassive black hole. But the rest of the galaxy is pretty much featureless and like egg-shaped, ellipsoid, or like a sphere or like an egg shape. And that's why we call it an elliptical galaxy. So nobody really understands how spiral structures form. I think there are two contending theories. And I don't know very much about galaxy evolution, but in terms of the appearance of galaxies, these are roughly the four categories. I mean, there is a lot of diversity in galaxies, and these are very rough categories, to be honest. Okay, so when it comes to spiral galaxies, they look very different depending on whether you're looking at them from the top uh, or from the side. With ellipsoidal galaxies, or so rather elliptical galaxies, they are just ellipsoidal in shape. So you don't see this kind of variation much. They just look like elliptical blobs. Um, but with spiral galaxies, you can actually see some difference. On the left is an example of what happens if you're looking at a spiral galaxy from the top, if you may use the word top, by that I mean like looking from the top of a dosa, right? And on the rightmost is what happens if you look at it from the side. Okay, on the side, see, like I mentioned, it's a pretty flat structure in comparison to its size. So you pretty much see this weak, in this case, weak central bulge and some dark dust clouds, and that's about it. Whereas if it's viewed from the top, or face on as we call it, you start seeing these spiral arms. So here I've shown you pictures. On the left is a face-on galaxy, as we call it. Here is something in between. This is Andromeda galaxy. It's viewed at an in-between angle. And on the right is an edge-on galaxy. So those are photographs. These are sketches. On the left is
Where is
triangular
my
galaxy.
ivermectin?
Yeah. Sorry? Is there a problem, or can I continue?
You can continue.
Okay. So on the left is a face-on example. This one's called triangular galaxy. It's almost seen face-on, so that's why you're able to see its spiral arms and so on in this sketch. In the center is something that is viewed at an intermediate angle. This one's called M106. It doesn't have a better name. And on the right is NGC 891, which is almost viewed on the side. And these are sketches, not pictures. Well, I told you about the four broad classes of galaxies and the face-on versus edge-on viewing angle of spiral galaxies. But galaxies are really very diverse. There are many galaxies like this that you just cannot classify. So for example, on the top left is a ring galaxy, which did not fall into any of the four categories. And the rest of them, I guess you can call them irregular, right? But they all have their own history and shapes and things like that. So, and their own peculiarities. So in fact, there are catalogs of peculiar galaxies. One famous example is ARP catalog of peculiar galaxies. So these are pictures from various telescopes, Hubble, and so on. These are pictures and sketches by amateur astronomers. So that the same ring galaxy that I showed you, this is a picture of it by Hemant in Texas with his 16-inch telescope. And here's a picture of antennae galaxies, a pair of interacting galaxies by Prabhu. And the rest are sketches. So you can see this is a sketch of an interacting pair of galaxies that I made with a very big telescope. You can tell all my sketches are very rough. I'm not an artist of sorts, but this is another peculiar galaxy. I don't know whether it is interacting or what it is, but it's called PGC 86395. No better name for it. And this previous slide I showed you, the cigar galaxy. This is a sketch of the same thing here by Howard Banich with his 28-inch telescope. And here's another peculiar galaxy, ARP 84 by Uwe Glan. So these are galaxies are extremely diverse and interesting. And I did mention the word interacting galaxy. What that is basically when two galaxies come nearby, you can think of a galaxy as a fluid made up of stars, if you like. So the gravitational pull of one galaxy pulls on the other galaxy and stretches this fluid. Okay, basically stretches the fluid of stars. And that's how you get all of these long tail-like structures. So this galaxy is sort of distorted by the gravitational effect of this other galaxy here. So this example is called NGC 6621. It doesn't have a better name as far as I know. And this is a Hubble Space Telescope photograph. In the center is a sketch by Howard Banach through a 28-inch telescope. And here's my humble sketch with an 18-inch telescope. I haven't been able to see the full length of this tail that we call a tidal tail of stars. But I've been able to see some. Howard in his 28-inch has seen the full thing. Yeah, so like I said, this one's called a tidal tail because it's caused by tidal forces, the same forces of gravity that cause tides on the Earth, stretching the fluid of stars, if I may. In the bottom left here is Rose Galaxy by Hubble Space Telescope. In the center is a photograph of the same thing made by Hemant with his 16-inch. I was amazed at how much detail he was able to capture. And on the right is a sketch by Howard Banach with a 48-inch telescope. So you can see that generally seeing things visually takes much bigger telescopes than photographing them. This was photographed by a 16-inch and it has more detail than this observation with a 48-inch. But photography has its own troubles, like tracking and processing and so on. So you trade out, you win some, you lose some, so to speak. The other interesting thing to note is that when these galaxies are interacting and the gravity of one of them is acting on the other and vice versa, they stretch this. They stretch the material such that it triggers star formation. And so you see a lot of these young stars forming. That's what you see in blue here and here as well. Sometimes this is called starburst. Okay, so galaxies form in clusters, just like stars form in clusters. I don't fully understand why, but I remember that they made this simulation called the Millennium Simulation or something. And they showed that clusters and superclusters naturally come from the dynamics of evolution of the universe. And so galaxies also occur in clusters. Our cluster, if you like, is called the local group. And there's a nearby Virgo cluster, there's the nearby Fornax cluster, and so on. This cluster is called the Hercules cluster. It lies in the constellation of Hercules. And the things that are points like this are stars of the Milky Way. And the things that are blobs like this are galaxies of the Hercules cluster. So it's a little hard to see in a black and white picture, but that's what we have. This cluster lies about 500 million light years away. Okay. So here, that was a photograph, and here are sketches. The sketch on the left is the same Hercules cluster by Howard Banach. In the center is a sketch of another cluster called Abel 151, which is 700 million light years away by Uwe Glan. And on the right is my own rough sketch of Corona Borealis cluster, which is 1 billion light years away with my 18-inch telescope. The yellow points are, I've marked stars. It's hard to tell when you're observing at high power and so on, whether something is a star or a galaxy. And so you just mark everything in your sketch and then come back and check which ones are stars and which ones are galaxies against an image. So I identified these as stars and marked them in yellow. And the rest of the blobs are galaxies. I've only seen the tip of the iceberg of this cluster because it's very faint. It's hard to see in my telescope. Okay. Now, the last thing is, yes, you can see clusters of galaxies. This one is kind of at the edge of visual observing, if you may. There is this phenomenon called gravitational lensing, which was predicted by Einstein's theory of general relativity. Basically, Light bends around matter, just like objects go around in orbits. Light also curves around matter, and the effect of this is that the matter acts as a lens and sometimes produces multiple images and arcs and such things. So on the left is a picture from a paper that I have linked here. And what it is that there's a foreground galaxy cluster called Abel 2152, which lies at about 580 million light years away. Okay, LTT stands for light travel time. So this galaxy is roughly like 580 million light years away. And because of its mass, the light of a more distant galaxy, which is 1.8 billion light years away, is being lensed. And the image that we are seeing of the distant galaxy is this thing. It's stretched out into a slight arc uh, that this paper has labeled A. And with a very large visual telescope, I was also there on this night observing with these people. Howard Banich made this sketch of this lensed arc. And I think he's one of the two people that saw it as extended. I just saw it as a point. But even this has not been spared. Even gravitational lensing can be seen with a gigantic telescope. But imaging it, I think Hemant has taken some pictures of gravitational lenses already. And I'm sure it is possible with the 16-inch to image these things. Okay, so there ends my talk pretty much. In conclusion, there are lots of very cool objects in the universe, and as hobbyists, we can enjoy them through observation, photography, and just learning more about them. And here are the artists whose pictures I showed you. And these are the people who took photographs. These are their faces and their equipment. And these are the people who made the sketches, their faces and their equipment. And here's me on the right with my telescope. Okay, at this stage, I'm going to stop and ask if there are any questions.
First of all, Akash, thank you so much. I think it was really interesting how you put out so many illustrations for us to see. And I think that's something we don't get to see often. So can you tell us more about this process of sketching and what exactly does it involve?
Sure, absolutely. So in a nutshell, the first step is to have a telescope, right, and take it to a dark sky site. And by that I mean really dark. I think the best place in India would be somewhere in the Himalayas, like in Ladakh, right? And there are some good places in the Western Ghats, but they are not as dark to do some of these things that I'm talking about. You can, of course, see Orion Nebula and such things, which itself is a lot of joy. So you take a sizable telescope to one of these dark sky locations, and the first problem is how do you find the object? Okay, your telescope has a tiny field of view that is sometimes much smaller than the size of the moon, and this object is invisible to the naked eye. So you have to point at something that you absolutely cannot see with your naked eye and bring it into this tiny field of view. So the technique that is done to achieve this is usually called star hopping. What you do is you identify patterns of stars. You start with a star that is visible to the naked eye, and then you go into your finder scope, which is a small binocular sized telescope mounted on your bigger telescope. So you go to your finder scope, and then you find that star, and then you find a few star patterns, and you look at a star atlas to literally hop from star to find the location of this invisible object. And then you center it in your telescope field, right? So you start with naked eye, and then you go to finder scope, and then you go into telescope. Okay, so then you have to know how to look. There is a special technique called averted vision. The funny thing is, we have never explored this range of our eyesight. Our eye is actually incredibly capable of seeing in the dark if you use the right techniques and you allow for it to adapt, and you know how to look in, or you know how to recognize signal from noise, if I may say so. So there's a technique called averted vision. First of all, you have to be fully dark adapted, which means that your eyes has to be completely in the dark for about 30 minutes, no bright lights. Once it is fully adapted, then you start seeing very faint things with your own eyes. And so then you use this technique called averted vision and look at the field, and you slowly gather information over the matter of a few minutes, and then you'll start seeing these blobs of light, and that's when you start sketching. You try and go back and forth between your pencil and paper and your eyepiece. You go back and forth and sketch whatever you can see. And sometimes you are slightly biased by the presence of an image. Sometimes you are not. Depends on how you like to do it. And then that's how these sketches are produced.
Okay, and I also was curious about this other thing. And I think each, visual astronomer has their own, I guess, ratio of observation versus astrophotography. Like
Mm-hmm.
sometimes they would prefer not to do any photography at all. So
Mm-hmm.
in your case, how has it been? Are you predominantly just an observer, or uh,
I think I am 90% observer, 10% astrophotography. Uh, so I did a little bit of astrophotography as a student at IIT Madras. That's the Trifid Nebula I showed you long ago. This was with an 8-inch telescope. But somehow I don't enjoy the astrophotography process as much. Now I'm also starting to do some more astrophotography because I found out that I can somehow do some photography with my big 18-inch, even though it's not designed for photography. So I am starting to do some, but I would say predominantly visual observing, a little bit of astrophotography. The only good image I've ever taken is that of the conjunction last year, Saturn and Jupiter.
oh, okay.
Yeah. Most of my images are not worth looking at.
Yeah, and can you quickly tell us about what telescope you own? Just
So let me go back to sharing my screen. How do I do that? Right, share screen. There, okay. So the telescope on the right is my telescope. So it is an altazimuth telescope in the sense that it is not pointed, that it's not designed to do photography very well. And it's a special design called a Dobsonian, which is used by amateur astronomers. In fact, all three telescopes here are Dobsonians. Mine is actually mounted on a tracking platform, this black thing here. This is my finder scope, and my eyepiece is actually hidden from view. It's a reflecting type telescope, which means it has a mirror, and it's an 18-inch mirror, and it's a Newtonian style telescope, which means that it has a secondary mirror here that just changes the light direction by 90 degrees, so that it's easy to observe. So I can go into more details if as needed. So yes, I mean, I confess that yes, most of what I've talked about involves a big telescope, like 18-inch or bigger. But that's not to say that you can't start out at least with an 8-inch. I started out with an 8-inch telescope. And for almost 2 years, I observed extensively with that 8-inch. Where was that? Long ago in this presentation. This was my first telescope.
okay. Okay, someone is asking, did you build that?
Say again?
Did you build that?
The small 8-inch telescope, I built maybe 50% of it. The rest of the 50% was done by Dilip Kumar and Vijay Kumar from ABBA. The bigger telescope, the 18-inch that I now use, I did not build that. That is made by a company called Obsession Telescopes.
Okay. All right. Yeah, so what would you recommend for people in cities? Do you recommend starting off with binoculars? Because,
Yes.
okay.
Yeah, absolutely. I think the universal recommendation, almost if you ask anyone who's done this for long enough, is buy a 10 by 50 binocular, which costs around somewhere between 3,000 to 5,000 rupees, and go and point it at go to a dark site. I mean, I think astronomy is more about, at least visual astronomy is a lot more about committing time more than committing money and equipment. At least that's my take on it. So you have to go to a dark site on a new moon night with which is clear, and then start scanning the sky with that binocular, and you will start seeing deep sky objects. You might not see a cluster of galaxies. That's impossible with a pair of binoculars, but you will start seeing open clusters and globular clusters and nebulae and galaxies, some galaxies, and it's an absolute joy to find these things. And the reason we recommend binoculars over telescopes is they are much more easy to maneuver. They don't have inverted view. You're not looking at an eyepiece which is mounted at 90 degrees. It's very it's much more straightforward to start with a pair of binoculars than using a telescope.
Got it. And yeah, I'm not sure if you talked about this, but a lot of people are curious about which are the best skies that you have experienced, and some of your experiences,
The
just
best size?
yeah, like where or which country have you had
Oh,
some of the clearest night skies?
oh yeah, okay. So I've only observed in two countries, which is India and the US, and and specifically South India. I cannot comment on North India because I haven't observed from North India. But I would say that the US has way better skies than South India, and it really changed the way I do astronomy, the sky quality. One of the reasons is we have a lot of moisture in South India. But then people who have been to Ladakh and the Himalayas have told me that the skies there are exceptional, and every bit of evidence I have tells me that the skies in Ladakh are going to be better than anything I've seen in the US. So I haven't seen them yet. I have to go and check for myself. But in the US, the best sky I have had is in uh, is in northeastern California, in a mountains called the Warner Mountains, and this was at 9,000 feet altitude, and it's really far away from any civilization. And I saw the West Milky Way and uh, things that I never thought I could see with my telescope, were visible. So that was a really spectacular sky. Um, it, it also varies from night to night. It's not just the place. The same place can have good nights and bad nights. And one of the best nights I have observed is that night that I observed at Lansing Arc. This was in Texas, and Texas in the USA. Those skies can get really dark. Unfortunately, in South India, we have a lot of moisture. So I have seen skies in Coorg, and they are pretty dark and pretty, but I suspect that transparency is not as good. And But I made lots of very good observations from Coorg as well. So if you ask near Bangalore, I would say the best sky is probably Coorg.
Got it. Yeah, I think it must have been an amazing experience to even just see the Milky Way. A lot of us have not experienced that because I don't know, we've just lived in cities our whole life.
I
So
know. I think everyone should try and see the Milky Way once, at least in their lives. And this can be done by going to the Western Ghats on a clear moonless night and just looking up, especially in the summer, and you'll see it.
right. Would you like to comment on CCD imaging and whether that is used predominantly, or have you dabbled with that?
Yes, sure. I would say that CCDs are these days primarily reserved for professional astronomers, because the technology that we call CMOS that exists in every mobile phone camera, every DSLR, it has gotten much better, and it's also very cheap. So uh, these days, I mean, imaging is mostly done by amateurs with CMOS cameras, and I mean, the easiest way is to start with a good phone camera, and I think there's an app called Gcam. I actually don't know, but you can take nighttime pictures, and both Android and iPhone have some sort of astrophotography mode. Um, and so you can take pictures with that to start with, or if you have a DSLR, you can take pictures with that. And a lot of the effort there goes into knowing how to set up things and make sure that your equipment is working right, and processing the results. A lot of processing needs to be done to get good images. uh, this is sort of what I know. I'm sort of a beginner in astrophotography. Uh, but I think the earlier it used to be hard to do astrophotography, but these days I think the entry level is much lower. You can do it. You can take very good pictures with just a DSLR camera, a lens, a good lens, and just put it on a tripod, take many exposures, and you can process it into a good image.
Got it. Yeah, a couple of final things. Do you, I mean, obviously, I guess you started astrophotography recently, but
Mhm.
how much of experience do you have in the processing part of it and, the image processing part of it? And I'm asking this specifically because I think when it comes to amateur astronomy, the processing is very subjective, right? It's not
Yes.
entirely scientific. So the aesthetic
Mhm.
component of the image
Absolutely.
is a very subjective thing. So the colors are not always very representative of, say, the chemicals or the gases that are being observed.
That's right. I don't have much experience in processing. I am sort of a newbie, and I do a minimal amount of processing with not so great processing tools. Uh, but you're right. The way that amateur astronomers process images is very different from the way professional astronomers process images. Professional astronomers are trying to extract scientific data, so they have to keep the linearity of the image and other parameters and the colors and so on to match whatever scientific result they want to extract. Whereas amateur astronomers are all about aesthetics. They will go to town and exaggerate the colors and all of that. In fact, there is even now a tool to remove the stars from an image. Just make the stars vanish and keep only the nebula. Some people like to do that.
Okay.
And yes, it's all about aesthetics, and it has its own value, in my opinion. I'm not going to, I mean, people might dismiss it saying it's not scientific, but this is the way we learn to appreciate the universe, right? This is what draws us to astronomy, these beautiful pictures. So, uh, yeah, but you're right that they are heavily processed. They are not fake, but they are heavily processed for aesthetics.
Got it. So is there anybody who would like to unmute and ask maybe a couple of questions?
That can do processing.
No, no,
Uh,
no. I was just saying anybody in the participants
Oh yeah,
who
right,
would
got
ask
it.
any other question. Yeah.
Sorry,
I
I'm
have
audio
one.
here. So
Uh,
Yeah.
I have one question. I don't think it is a good question, but I just wanted to ask. Uh, do we require some coding background for processing photographs?
for processing, no, but you need to know your image processing operators and what they do. So the people who process, so all the coding part is already done in software tools like PixInsight and so on. But you need to know what tools to apply and what they do. So for example, there are tools with funny names like histogram equalization, dynamic background extraction. I actually have never used any of these, but I've heard these words. so so there are various noise reduction methods and various uh, methods to pull out detail and brighten the image and all of that. And you need to know what each of these tools do, which you can do by trial and error, which you can learn by trial and error. But I don't think you need to know how to code.
Okay, okay. Thank you.
Yeah, sure.
Right. Is there anybody else who would like to ask any questions? Somebody has asked, are there any GRPs who travel to look into these deep space objects?
Yeah, I think he means groups, right? Yes,
Group. Oh, okay.
I
Okay.
I know that Bangalore Astronomical Society regularly organizes something called a star party, and this is essentially a gathering of amateur astronomers. Usually, it's done in Cork. Uh, so it- they either carpool or organize a bus or something like that, and there'll be a few people who bring telescopes, and they all observe or photograph depending on what they're doing. And usually, yes, it's deep sky objects because planetary you can kind of do from Bangalore. If there is a new comet in the sky or an old comet that is visiting, then of course there's going to be some attention to that. But mostly it is deep sky objects. Yes.
Akash, I have another question.
Yeah. Go ahead.
Uh, what exact catalogs do you refer?
So the best catalog for beginners is a catalog of 110 objects called the Messier catalog, Messier. It's written as Messier, but it's a French name. That's why I say Messier. Uh, so the Messier catalog has 110 bright objects, and this includes favorite things like Pleiades cluster, Andromeda galaxy, Triangulum galaxy, and Orion nebula, and all of these. So these are all part of Messier's catalog. So if you look at any introductory book to night sky observing, like one of P. N. Shankar's books or Edmund Macphy's Sky Atlas or any of those, then you will actually find Messier objects plotted there, and then you can try and find those. So if you want a catalog for beginners, then Messier is the best place to start with. And then there are more advanced and more challenging lists like Herschel 400 and the entire NGC, ICE, and so on and so forth. But Messier is the
Uh,
place to start.
is there a planet that exists like our solar systems? Because I believe that Earth is not just the only solar system that like exists in the main solar system. So is it possible? Is there a possibility that another what it called solar system that exists in space?
Did I get the question correctly? The question is there a possibility that there exist other solar systems in the universe?
Yes.
Yeah, absolutely. These are normally known as exoplanets or exoplanetary system. In fact, there's a space telescope or something like that called Kepler that is dedicated to finding these. And they have found many, many, many planets orbiting other stars other than our sun. And the word to look for is exoplanets.
Okay. I asked this question because many of the what do you call many of my friends keep talking of what you call aliens and stuff like. So I just want to ask any plan but not
Sorry, your voice is breaking, at least for me. I don't know if it's a problem at my end or your end. Can you type the question?
Yeah, it was breaking for all of us.
Oh, okay, okay. I think the point was about alien civilizations, and that's a question that that's a very speculative topic of research that I don't have much expertise to, but my opinion on this is that alien civilizations almost surely exist, given how big our universe is and how tiny we are. That's my opinion, but of course we haven't heard anything, and there are various theories for why we might not have heard from alien civilizations as yet. Of course, we don't know. I mean, it's possible that our physics is also limited in our in our ability to think of these things. But my personal opinion is that they probably exist. But yeah, it's a very interesting open question.
Akash, I have another question.
Yeah.
People say that it is difficult to find exoplanets or discover exoplanets. Why is it so?
Because you don't have it's so See, a star, first of all, exists pretty far away, some of these stars. And you're trying to find something that is extremely close and extremely faint compared to the star. So you're trying to find a very faint object next to an extremely bright object. And that has its own challenges. So the way most people, the way I know that some of these exoplanets are found is when this faint planet, planet doesn't have its own light. So when this planet comes and crosses the front of the star as it orbits the star, then there will be a small dip in the light that we receive from the star. And this dip in light is what is one method of finding exoplanets. I think there is one more method, which is to use the spectrum and Doppler shift and so on, but I'm not an expert in these things. But the reason that I understand, in my understanding, the reason it is extremely difficult is because you're trying to find an extremely faint object next to a very, very bright object. So that's very challenging, because if you try to expose very long, then your bright object will fill the field and you won't see anything. And these planets are going to be extremely faint. So it's almost impossible to see them directly.
On those lines, what is the most challenging object that you have observed visually?
Uh, I would say it is the gravitational lens of the galaxy that is 1.8 billion light years away, that was lensed. I showed the very last. I would say that's one of the most challenging things I've seen. There are some other things like that, and they usually tend to be just very distant galaxies. Uh, like I think when you start trying to look for individual galaxies that are not so-called quasars at 1 billion light years away, then they tend to be extremely faint. So uh, those are some faint things. I can't remember what is the faintest. I don't know if there exists a faintest thing that I have seen, but because it also depends on the telescope, the sky conditions, and so on. But I would say that that lensing arc was very, very faint. Yeah. The funny thing is, it does not correlate very well with distance, because there are things that are as far as 3, 4, 5 billion light years away that you can see very easily. And that's because those are galaxies with extremely active cores, where there's a supermassive black hole that is really, really doing very violent things. And so even if the galaxy is 7 or 8 billion light years away, you can see it with an 8-inch telescope. Maybe not 7, 8, 3 billion light years away, you can see it with an 8-inch telescope. So uh, those are really fascinating, but they're not the hardest observations.
Got it. And yeah, we had a recent conversation where people were asking about stellarium and its relevance in actual, or its use perhaps in visual astronomy. So do you use stellarium as a tool often, or is there anything else you use?
So I use a software called K-Stars, partly because that's what got me into astronomy, and I also became an open source contributor to that software. So I actually have code contributions to it. So I'm sort of partial to it, and I put in a lot of features that would benefit my workflow into it. So I use K-Stars instead of Stellarium, but for beginners, I would definitely recommend Stellarium. It is, or even on Android phones, there is an app called Skye, Skeye, which is developed by a friend of ours named Harshat in Belgaum. It is one of the best apps on Android, I'm told. And on iPhone, I recommend Sky Safari. And both of those apps have the ability to, you just move your phone, it'll take you around the sky. I think those are better than Stellarium for beginners, but for people who are more advanced observers, then I think you would prefer to use Stellarium or the other apps like Carth2CL is another app, and K-Stars is another app. So as depending on your experience level, I would say that Sky and Sky Safari are the easiest to start with. Mobile apps, basically.
Okay, I think we'll definitely check K-Stars out. That's something we've not explored yet.
Sure.
Okay. Cool. Are there any other questions from the audience? By the way, I'm sorry, but we were not. I mean, we did not give you guys permission to unmute so far. I was not aware of that. But I think right now you do have the permission. So if there's anybody who wants to, you can do so. Yeah, I think no other questions.
Okay. Thank you, Sitara, for this platform. And I know you had you went through extraneous circumstance, sorry, like difficult circumstances to make this talk happen. So thank you for that. And
No, I have to thank you because I think you put together such a fantastic presentation. So yeah, we've all been waiting for it, and we would love to have you here again because a lot of us are also just getting started, and we do want to learn the more technical aspects of it.
sure,
So
absolutely.
yeah, we would love to have you again if there is anything you feel you could, explain or talk about. So
Sure.
okay, thank you so much, Akash. It was
You're welcome.
really a pleasure having you. Yeah, thank you.
Bye.